for those of you remote and those of you who are here, thanks a lot for coming. This is the last class of the year. It's a lot about comfort. This is one of my favorite topics. It seems like as HVAC people, we are very driven to be code compliant, and often we miss the mark on making our clients comfortable, which is too bad. There's going to be a lot here today that Price has put together in the background. You know, we do lots of overhead mixing in, well, I think across the nation, we do lots of overhead mixing, and we're going to poke a little bit of holes in that gold standard that we've been using for a lot. Oh, there's Caleb. Caleb, you were going to do this, but I got impatient, so sorry.
No, I thought you were. Sorry.
Oh, we're all good. Yeah, we're on the same team. So we have a few folks here from Price today who are going to be presenting, and then we also have some folks who are going to be, well, there's Sandrine. She's going to be remoting in and taking the first section. So since we're a couple minutes late, I'm going to have her take over, and then you guys just all introduce yourselves when you get up, and let's get started. And thanks again for coming. All right.
The last thing I will say, interaction is asked for, is
Demanded.
There you go. We have raffle tickets, so if you're asking questions or making comments, you'll get a raffle ticket for.
Pretty nice.
You're up, Sandrine.
Okay, awesome. Just a heads up, Elizabeth, I was not able to hear what you said, but it sounded like it was important and intelligent. But let me just get started. I'm Sandrine Delacqui, or Sandrine Delacus, for people in the United States. I am the Senior Product Application Specialist for the Grills, Registers, and Diffusers team at Price Industries. And today I'll be talking about mixed air systems and how to make sure that people are comfortable when you're designing different rooms. So I am part of a larger team. We're a team of 5 at Price Industries, and all we do all day is answer emails, phone calls about how to use our products, so how to use grills, registers, and diffusers, where should you use them. And we also do a lot of research behind our products just to make sure that we're giving the reps and the engineers and the contractor the best information possible. So today, the agenda of the day, we'll do the basics really quickly: room air distribution, grills, registers, and diffusers, airflow performance, and then we'll dig into maybe the most common scenarios that we see, which would be small spaces like an office, a hospital room, and then we're going to dive into large open spaces. And I guess for those that are live, feel free to ask questions, and Elizabeth can relay the questions to me. For anybody who is participating remotely, I do have access to the questions and answers, so feel free to type in there, and then when I see it pop up, I'll try to answer as quickly as possible. So diving into room air distribution. So typically when we're talking room air distribution, there's going to be 3 different systems that you'll hear about. You'll hear about a fully stratified system. So this would be something like a displacement system. You've got a source here that has very low velocity air coming out, and it's seeking the heat sources, and then all of the contaminants are basically coming up to the ceiling. So at the ceiling level, we're going to have a lot more contaminants, a lot more heat, a lot more stratification, really. The next system we're going to see would be something like an underfloor system. So again, we're going to see some stratification, but in the occupied zone, there is going to be some mixing. And then lastly, we've got our fully mixed system. So that's the system that I'll be talking about today. I'm the expert in this type of system, but later on today, you'll hear from Mike Kupriyanov and Narayan about the other types of systems. When we're talking about a fully mixed system, that would mean that at the floor level and at the ceiling level, there's going to be the same amount of contaminants. So the same amount of CO2, the same temperature at the floor versus the ceiling in an ideal fully mixed system. So how does a mixed system work? Typically, you're going to have a ceiling diffuser, and that ceiling diffuser is going to have your primary supply air, and it's going to come out of that diffuser at a really high velocity. That's going to create some pressure differential, and that pressure differential is going to do two things. The first thing it's going to do, it's going to pull that room air up. So it's creating a high velocity, and it's going to pull the air around that primary jet up, and that's going to start moving all of the air in the room. The second thing that high velocity air is going to do is it's going to cling to the ceiling. And you're often going to hear that as the Coanda effect. You hear it a lot in HVAC. That's just the tendency for air to cling to a surface. If you open or if you watch TV, and if there's any other girls in the room, I feel like nowadays I hear the Coanda effect talked about all the time for like those Dyson air wrap. Same idea here, but with a diffuser. So again, the high velocity air comes out, it's going to make it across the room, and as it goes away from the diffuser, it's going to lose momentum, and it's going to mix more with the room air. So once we reach the occupied zone, ideally your air, which was probably 55 before, has now reached room air, so 75 degree, so that when it does come into the zone, you're not going to be able to feel a temperature difference. What we're really wanting to make sure is at the right temperature and without high velocity would be our occupied zone. So that's defined by ASHRAE as the area that's 6 feet from the floor, 1 foot from any interior wall, and 3 feet from any exterior wall. So basically, we're assuming that people aren't that tall and that people aren't spending too much time against a wall. I will say that the 6 feet is not that hard to comply with. The 1 foot and 3 foot from any exterior wall can be a little tough. In our offices here, we do have desks that are mounted right against a wall. So just because this isn't included in ASHRAE's definition doesn't necessarily mean that you shouldn't try to reduce the velocities at those walls, especially if you know that you're going to be installing some furniture up against the wall. So how do we condition the space for an air mixing system? So typically we're going to see either grills, registers, or diffusers. Grills are typically pretty simple. It's a device that covers an opening. Typically there's going to be some blades in it, either fixed or adjustable, and typically the grills will be used for both supply and return air. So typically very simple, the air comes out directly out of the grill. There's not as much to think about than something like a diffuser. When we're looking at grills, typically fixed deflection would be a return, and then anything that is adjustable, either one way or double deflection, would be for supply. And a lot of people often ask, why do you even have adjustable blades? What is the point of these adjustable blades? So often the blades are going to be used to adjust the throw of a diffuser. So if you have your blades set to 0, you're going to have your longest throw with a very narrow pattern. As soon as you start to adjust the blades, you're going to have a shorter throw with a wider pattern. And again, if you adjust them even more, even wider. So this is going to, if you do adjust the blades, that's going to ensure that you get that shorter throw, and it's also going to get more mixing near the diffuser. This is very good if you are installing it in a sidewall and maybe you have a smaller room. Typically, that's when you want to start adjusting those blades.
Successfully adjusting blades in the field, and I think most engineers said No, they're not. Unless they're specifically asked to.
Yeah. And I would say, I don't know if other people are talking, I would say it's the same for slot diffusers. Often slot diffusers, and we can get into it later, will have a setting in mind, whether it's horizontal or vertical, whether that is ever getting adjusted. I don't know that anybody is ever adjusting it until we get a complaint that it is drafty or that it is cold. I'm sitting under a slot diffuser right now that definitely was not adjusted, and I'm freezing. Okay, so awesome. Continuing, so that's typically your grills. When it comes to diffuser, it gets a little bit trickier. There's more things to think about. The definition for a diffuser is any outlet which discharges supply air in various directions and planes. Basically, the air typically out of a diffuser will either come out perpendicular or vertically, but you'll have more options for throw pattern, for whether it's radial or modular or directional. Typically, there's just a little bit more engineering that has gone behind that product. In general, when we're comparing a diffuser and a grill, the diffuser is going to entrain more of the room air, and that's going to give you better air movement in your room compared to a grill installed in a sidewall. Looking at the different types of diffusers out there, I think everybody is familiar with this one, a radial pattern diffuser. So that would be something like a square cone diffuser or a square plaque diffuser. I feel like anywhere you go, you're going to see a square cone or a square plaque diffuser. They are very good. They are our bread and butter. They're good because they have short throw lengths. They're not impacted by poor inlet conditions. And typically, if you're looking at most spaces, a square plaque or square cone diffuser does a good job of mixing the air and cooling without causing too many drafts. But later on, we'll see the different options that we have instead of just always using that square cone or square plaque diffuser. The next type of diffuser we often see would be a directional pattern diffuser. Like the name says it, the directional diffusers will have the air coming out in certain directions. Typically, you'll have the option for either 4-way, 3-way, 2-way, or 1-way pattern. Often, we're going to see these in rooms with taller ceilings or in rooms where you really need that direction. So often in hallways, we'll see a 1-way diffuser used or even a 2-way diffuser used going with the air going opposite ways. That's just going to ensure you get to cover the entire hallway without creating drafts by having the air come down the sides of the walls. The next diffuser we're seeing more and more would be a high induction twist or a twist diffuser. People also call them swirl diffuser because of their swirl pattern. It basically looks like a little hurricane when the air comes out of the diffuser, like we saw in that first smoke video. So this is going to be used in applications similar to where you would use a square plaque or a square cone diffuser, but typically because it has that swirl pattern, it has more turbulent air and the air coming out is at a higher velocity, is going to do a quicker job of mixing the air in the room. So typically this is going to be used especially in those low temperature applications or areas where you want that air to mix immediately so that we're not causing any drafts. And then the other two types of diffusers we'll see is nozzle diffusers. Nozzles are a little bit more niche than the other diffusers because there's not that many applications that work well for them. They have very, very long throws. So typically we're going to see them in large open spaces like atriums or even airports. And architects always just really like the look of nozzles. So that's why they come up more and more. And then lastly, we've got a slot diffuser. Slot diffusers really are used in all of those architectural spaces. They typically have the option for horizontal or vertical throw. There's typically also, most manufacturers offer different pattern controllers. But as mentioned previously, one of the big challenges that we are facing is people are not adjusting the pattern controllers. So maybe it was set to have the air come out to the right, but nobody has adjusted that pattern controller and it's set to come out to the left. And when that happens, that's just going to create some uncomfortable spaces for people. It's very hard to tell who should be adjusting these. It's always a kind of a fight between the balancer, the mechanical contractor. Nobody really wants to adjust these and nobody really knows who should be adjusting them. So often on specs, I'll actually recommend that people write who should be adjusting these. Usually when I say this comment, somebody in the room chimes in as like, why don't you just adjust the pattern controllers for us? We have tried to do that in the past where we've shipped a diffuser with pattern controllers set a certain way. But the problem is that with the transporting of the diffuser and all the shaking that goes around, just because we've set it one way in the factory, it doesn't mean that that's how it's going to come at that job site. Some diffusers can also be installed flipped, so it would be very hard to coordinate that and to make sure that nothing shifts during shipping. So we did get a question. Who do you most commonly see taking lead on setting the slot diffusers? The balancer, the mechanical contractor, or another entity? Honestly, I would say that nobody is really taking the lead. I've seen some schedules where they will call out the balancer to adjust the pattern controller, and I have seen some where they call out the mechanical contractor. Typically, the engineer will have a conversation ahead of time. To me, both make sense, but sometimes I feel like the balancer might be a good person to do it since they're most likely already going in there and adjusting some sort of damper. So it might be worth it to also adjust the pattern controllers at the same time, but it will depend on your relationship with the mechanical contractor and the balancer and kind of how that plays. Tom, do you guys typically see one or the other used in your area, or anybody else in the room for that matter?
Tom shaking his room. Anybody else? Tom shaking his head. Anybody else in the room? You specified testing and balance contractor. Okay. Anybody else do it differently? Okay. So balancer is the answer here. Anybody else? Just show an airflow arrow and hope it gets done. I love it.
Oh, that's hilarious. But yeah, I mean, even here, the pattern controllers weren't adjusted. So just because I'm pretty sure we had somebody state how the pattern controller should be adjusted doesn't mean that it happened. So I'll probably get up on the table after this conference call and adjust them myself. Okay, so that basically sums it up for the types of diffusers. So let's quickly get into the performance so that we can dig into those special cases. So when we're looking at the airflow performance of a grill and a diffuser, what we're typically going to see on performance is the throw of the diffuser. So typically that's going to be listed as 150 feet per minute, 100 feet per minute, and 50 feet per minute. So as the air moves away from the grill or the diffuser, it's going to slow down. So that 50 feet per minute throw is always going to be that longer throw. In some cases, like a grill, will also list the spread. So if you are using those blades to adjust, we will list the spread for different angles. So looking at a grill, when we're looking at the performance page, typically we need to know either the core area or the nominal duct area. Most likely it's going to be your nominal duct area. You're going to have an opening. It's going to be 12 by 12. And so you know you need to order your grill 12 by 12. So when we're looking at the performance for this grill, we're going to see the static pressure, the velocity pressure, and the total pressure. Typically, two of them will be listed and the third can be calculated. And then we're going to have airflow, throw distance, and sound. This would be a typical catalog page. Typically, the nominal duct will be on the left-hand side. And then because the area of these grills or the core area of these grills are similar, they're going to be lumped together. That's just going to allow us to catalog a lot of grills with less catalog pages. And so grills that have a similar core area will have similar performance, and typically we'll have it listed by core velocity. And then we'll have the throw values, again, typically 150, 150 feet per minute. What you'll see in most catalog pages for us and from other manufacturers is that our grills and our diffusers are tested as per ASHRAE 70. So what does that mean? ASHRAE defines the testing method for all grills, registers, and diffusers. So they're telling us how we should test our grills so that we test our grills the same way that Titus tests their grills, the same way that Metal Air or Nailer tests their grills. And that way we can get repeatable performance. But because of this way of testing, there are some conditions that we just know aren't going to be happening in the real world. So one of the things is isothermal air. So isothermal air just means that the air that coming out of the diffuser is the same room temp as the room temperature. So there is no temperature difference there, but we know that in any real application, that's not going to be happening. So later on in the presentation, we'll go over how we can deal with this and how we can use some correction factors to adjust for air and cooling or air and heating. We're also assuming non-turbulent smooth inlet conditions. So that means 3 straight duct diameters. That's never happening in the field. So that's why typically when you're selecting a grill or a diffuser, you want to select it with lower pressure drop and lower NCs than you typically want, just to make sure that you're taking into account that it's not installed as per tested. And when you're looking at performance pages, you just want to make sure that the most current version of ASHRAE is being used. There has been some changes, so you just want to make sure that the most up-to-date version is being used. And this is going to be true for diffusers and grills. When
Sandrine, hang on 1 second.
Sorry, I need like every time you do it, you like jump scare me. I need like a little like.
All right, I'll ask the question again. I just asked what no problem, what the engineers here like focus on when they're doing selections, and if you're using all-in-ones, actual data, or if you're going off the catalogs. Dave said they do look at NC and pressure drop. That's the main 2 things. And then obviously, depending on the application, the throw is something they're looking at as well. Mm-hmm. Right. Okay. Right. Unless it's some sort of special application where you need something that's not a rule of thumb that you've kind of established. Right, okay. All right. You can continue.
I feel like I'm missing out on all the good conversations. Now I have FOMO. Okay, so looking at something like a diffuser, we're going to be looking at very much the same performance as a grill. You're just going to see it laid out a little bit differently. So typically it'll be laid out by your neck size, so your duct size, and the face size. Most likely probably like a 24 by 24 because that's what most ceiling tiles are. And again, we're going to have the static pressure, the velocity pressure, and the total pressure will catalog too, so that you can always calculate the third. And then again, we're going to have flow rates, throw distance, and sound. The way that it's laid out is going to be a little bit different. You're going to have your face size at the top with your inlet size along the left-hand side. And then again, you're going to have your neck velocity so that you can make your selections. Typically, when you're making a selection, I typically stay within the 500 to 800 feet per minute range when selecting a grill or diffuser. That typically is going to allow you to have some low pressure drop and not too high of sound. When you go over that 800 mark, I mean, when we're looking here, it's not too bad, but once we get to the bigger sizes, we're starting to get a little bit more pressure drop and sound that might not be okay if you have multiple diffusers in your room. And again, here we're going to have the throw, and it's going to be listed as 150 feet per minute. Like you said, in most cases, a grill is really going to be selected by NC and pressure drop, and the throw is a bit of an afterthought. They're like, good enough. Or, oh, you know what? I've used that square plaque diffuser at another job and I didn't get any complaints, so must be good to go. And that can work in a lot of applications. You know, the rules of thumbs are there for a reason. But if you do have some rooms where maybe comfort is key, if you're designing maybe like a high-end home where it gets like a little bit more, people might complain a little bit more about drafts, that's when you want to start to really look at that throw performance. The main way that I see the throw performance used is by doing throw mapping. So throw mapping is just the idea that you take that 50 feet per minute throw and you want it to hit right above the occupied zone. So right above 6 feet from the floor. So basically you are laying out your diffuser so that the 50 feet per minute throw goes along the ceiling and then comes down, and that total length will equal the throw that was listed in the catalog pages. And you would do the same for two diffusers side by side, but you would just figure out half the distance and then the vertical distance down. Why is it 50 feet per minute? Is typically a question that we get asked. 50 feet per minute is more or less the limit of when you can still feel air on your skin. So because we're setting it right above the occupied zone, we know that when it does reach the occupied zone and where people are standing or sitting, the air is going to have lost even more momentum. So the velocity in your occupied zone is going to be less than 50 feet per minute. So there shouldn't be any drafts in your occupied zone. So that would be typically the first way or the main way that people
We got
will look. Yeah,
another question.
yeah, love it.
Yeah, characteristic of air would be the same heating mode and cooling mode.
So the question was, is the characteristic of the air the same in heating and cooling?
No, we're going to see that the throw will change in heating and cooling, but you are kind of stealing the show here. It is coming up in, I think, a couple slides. Well, we'll go over how to deal with heating and cooling. So before we get into like the heating and cooling, let's quickly do the small spaces, and then we'll get into like the nitty gritty of how do you condition a space when you have heat cool, and what are some rules of thumbs and different things you can use to help. So one of the first spaces that we typically see would be small spaces. So that's typically offices. The main challenges we have here is the small footprint. We're always fighting for ceiling real estate. There's typically not that much room. There's going to be lots of light. There's going to be a supply or return, typically some sort of sprinkler, and more often than not, something else in your ceiling. So we're really trying to fit any diffuser in this space. The next thing we're fighting against is hard surfaces. Because you have walls all around, you typically have some sort of desk and some sort of shelving unit. The room can feel a little bit louder because there is so many hard surfaces. We're typically dealing with some sort of obstruction here. We've got a desk, not a desk, a shelf here, so that when the air comes down and hits the shelf, it's going to fall down and it's going to be pretty near this lady. If that shelf was maybe a little bit higher, then maybe we would have less of a draft on this lady at the desk. And depending on what type of office you're dealing with, you might have some high solar load. So if you're doing an interior office, like the office I'm in now, that's not going to be a big deal. But if you're doing a corner office where it has glass all along, it can be tough to design for because of those high solar loads. So just taking a look at a couple different offices, the first thing that we notice is they all use the square plaque diffuser. The square plaque diffuser is great. It's great in cooling. It's going to give you good pattern. It has short throws or shorter throws so that when the air gets into your occupied zone, it should be mixed and it shouldn't cause too many drafts. So if you're looking at a typical office layout that we have here and that we saw in some of those photos, you've got a desk, probably someone working at that desk, a couple chairs, and maybe some sort of shelving in the back. And typically, this is what we're going to see. We're going to see a square plaque diffuser smack dab in the middle of the room. And if that was the case, that would probably be a pretty decent design. I wouldn't have any qualms about it. I think that you would get probably pretty good air mixing. My only issue with this type of layout is just because the diffuser on the plan is getting showed in the middle of the room, doesn't mean that's where it's getting installed. In some of the photos you saw over there, we had a square plaque diffuser against the wall in the offices. Here we have our diffuser more in this corner here. Really, because there's so much stuff in that ceiling, the diffuser almost never gets installed centered perfectly. And because it's not centered and you've got a radial pattern, that can cause some drafts. So we just need to be careful about, should we always be selecting the square plaque diffuser? Is that our best option? And is that going to ensure that people aren't going to be feeling drafts? If we look at a square plaque diffuser installed against a wall, especially in cooling, that air is going to hit the wall and it's going to keep moving down. This was a mock-up for a patient room. And in this case, because the diffuser was installed so close to the wall, the cold air was dumping and coming, or not dumping, but it was coming down the wall and going directly on that patient. So that cylinder here is mimicking a patient. So it has a heat source that is being used to mimic somebody laying on a bed. That's very important to think about when you're laying out your diffuser. Here, this person in a hospital is probably not wearing that much clothes because they are in the hospital, and now they're getting air dumped directly on their head. So that could also be said if you had an office where maybe you had the desk right against a wall. Now that you've got the desk right against the wall and maybe the diffuser wasn't installed center, the air is coming down, maybe it's blowing your papers, maybe it's creating a draft to whoever is sitting there, or maybe your chair is pretty close to that wall. And again, your diffuser is not centered. Again, those are some times where you're going to get a draft. So what can we do in these types of situations? What I tend to recommend in these types of situation will be a high induction modular diffuser. So the high induction modular diffuser is basically a modular diffuser. So it has a direction to it, but the high induction part means that it has some vanes in the diffuser, and that's going to create some turbulent air, and it's going to mix the air faster than your typical modular diffuser. So in this case, especially if you know that you're fighting for real estate in your ceiling, installing a two-way diffuser where now you have some options to install it in some of the corners and have the air move across the room and across here, and nothing that is going directly against the wall near wherever your person is sitting should allow that client to have good thermal comfort. You could also look at a three-way diffuser. Again, same idea, where you're not getting the air to hit the wall at a high velocity, so it's going to come and hit the person that is sitting directly below the diffuser. So although a square plaque diffuser can work in a lot of cases, when you do know that you're cramped for ceiling space, getting a diffuser that has a direction to it can ensure that it can be installed in a way that everybody will be comfortable. And we did do a little bit of testing on this. This was with, again, a patient room, but really a patient room ends up being a lot like an office. It's going to be very small. You're going to have people sitting in there for a long amount of time that might be more prone to drafts. So here we had our hospital room, we had our bed, we assumed somebody was on the bed and maybe somebody was beside them. And then we had a window. The idea here was we wanted to condition the whole room and heating and cooling and not need radiant heat. So there's two alternatives that were found. One was using a three-way high induction diffuser, and the second was using a two-way high induction diffuser with a linear slot. Because again, we had tried that square plaque diffuser and we just didn't have room for it in the middle of the space. So we were trying to find an alternative a diffuser that could be installed closer to a wall. So this is just the example of a high induction directional diffuser. So you see that it has that four-way kind of a design. But because of the high induction vanes, you get more distinct jets, and it ends up being a little bit more of a radial pattern. The air coming out is going to be at a high velocity, and it's going to be very highly turbulent, and that's going to allow the room air to mix much faster. So if we look at our hospital room here, we had our slot diffuser here, our modular diffuser in the ceiling. We had sensor trees, so we were measuring every 12 inches the velocity and the temperature, just to make sure that in the occupied zone we didn't have excessive velocities and that we had good temperature control. And then we had our two dummies sitting beside the bed. So if we look at the first alternative here, we have the high induction three-way modular diffuser. The current is closed here, but we did do a test with the current open and closed. And we did see that in heating, this worked very well. So if we look at our heating values here, We had low velocities in right beside the window and at the bed, and we had relatively good temperature. We were trying to hit 74 here. The problem here was in cooling. A lot of times in heating, you're going to have a lower CFM than in cooling. And in cooling, typically your throws are going to be longer. And we really saw this in this example where in cooling, we had very high velocities that were most likely going to be uncomfortable for the patient, as well as anybody standing next to that window. So instead, we looked at our second option.
Hold on one
here.
sec.
Yeah,
We got another question.
love it.
A lot of times in an environment like there, we really can't reduce the heating elements because of the air change rates that we need to maintain in there. So did you happen to model something where we did have the same velocity across cooling and heating?
In this case, we did not. We
Do
only
you want him to
modeled.
state that again?
Yeah, sure.
Oh, you're muted now for some
Me?
reason.
Am I still muted? What about now?
I don't know why we can't hear you.
I don't know. No, no.
Go back to that and then click
Oh, Brandon
the
can hear me.
room audio. That should be fine, right? Speakerphone. Zoom can hear you, but we can't for some reason.
Okay.
Yeah. No. And here, I don't think this could turn off the sound. Just click change the speaker. Okay, try talking now.
Hello, can you hear
Hey,
me
there we
now?
go. We're back. All right.
Hey.
All right. So Dave, do you want to ask your question again?
Just, I know that you had a reduced amount of volume when you went into the heating mode, but with our minimum air change rates that we need to hit in patient environments a lot of times, had you happened to model that with the same volume for both cooling and heating?
I think in this case we didn't, but I have seen other jobs where we have used the same airflow and heating and cooling. Typically those are a little bit easier to condition because here in cooling we had, I think it was something like 400 CFM, but in heating we had 200 CFM. So it's really hard to get that hot air down versus if you can have the same airflow and cooling and heating because you have more air and more momentum, you're going to be able to get that air closer to the occupied zone. So for this particular application, we didn't, but I think that like, I don't know, Mike, somebody in our CFD team, he did model that not too long ago. So if we want, after this webinar, I can try and find an example where the heating and the cooling airflows were the same.
Sounds like it's just improving that condition, right? With the people.
Yeah. Yeah, really, like if you, in an ideal situation, I would try to have my supply or my cooling and my heating at the same airflow. And also I would try to get my heating temperature as close to the room temperature as possible. So really trying to minimize the delta T, so the temperature difference between your heating and your room. That's really going to help really mix the air well in heating, because that's our biggest struggle, right? In heating, the hot air wants to stay around the ceiling, versus in cooling, it'll naturally just come down.
Okay. If you want to tackle the Q&A questions,
Yeah.
feel free to do that. You want to pull them up?
Yeah, I'm looking at them right now. 2 of them were just telling me that they could hear me on Zoom. So we're good for those ones. And then we did have a question. Does the location of ceiling mounted return air grills affect the performance of the supply air diffuser? Really, in general, where your return air grill will have very minimal impact on the whole air moving in your room. But there are some locations that you want to try to avoid. Those locations would be directly beside your diffuser. If I can, here. So if you install it directly beside your diffuser here, I mean, that's kind of, if you think about it, just not a great idea. The air coming out of your diffuser coming out at a high velocity is probably just going to go right over your return grill, and your return isn't going to be doing much. The saying being said, if you install your return grill maybe a little bit further, but still in line with your supply air grill, the air coming out of your diffuser is going to go along the ceiling and it's going to lose momentum. And then it's going to lose enough momentum so that when it gets to the return air grill, it's just going to swoop into your return. So really just trying to make sure that the return grill is not located right beside your diffuser. In heating, we did find, or ASHRAE has found, and through mockups and CFD, we have found that installing your returns in a low sidewall opposed to a ceiling can help a little bit. It's basically forcing some of the hot air down. So if you think about it and you had a return grill in your ceiling and heating, all of your hot air is rising. So it's going to rise and it's going to rise in your return air grill. And basically you're not going to be heating the room. If you do have it lower, well, the only way the air is getting out of this room is through that return air grill. So it can kind of help get some of that heating down. It's not doing a huge amount of work, but it will help with your ventilation effectiveness. So it will help make sure that the room is mixed well. Perfect. And then just zooming through this because I don't want to take up too much time. So really, when we're thinking small spaces, a radial pattern diffuser can be very good, but it's not always the best option. If your ceiling is cramped, there are other options out there. If you are going to condition in both heating and cooling, again, having a diffuser that is going to have high induction is going to work well for mixing your room. And if we can get the supply temperature to be close to the room set point and have more air, that's going to be even better in heating. And let's dive into those large open spaces because that's where we're going to see really the effect of hot versus cold and kind of some of those rules of thumb. So when we're dealing with large open spaces, so we're talking a school or maybe an open office, some of the challenges we have here is getting full coverage of the space. It is very big and typically we have a lot of air to move. Maybe there's cubicles or obstructions, so making sure that everybody is conditioned can be a challenge. Again, fighting for ceiling space. Here we've got a nice office, but we have some wood slats. It's always a challenge when we're working with maybe a little bit more architectural ceilings. There can also often be changes in ceiling heights if you've got a drop ceiling and then a bulkhead that can create some drafts. And then the main one here is if you've got an open office like this one, or even in our office, is we have windows. So we have a perimeter zone within our open office. So how can you condition this in heating and cooling while you have a perimeter zone? Typically, when we're looking at these spaces, like we see here, we've got a square cone diffuser, could be a square plaque diffuser. Really, this is going to work great in cooling. So if we look at a square plaque diffuser, a full flow in cooling, you're going to get really good pattern out of it. The air will go across the ceiling, it'll drop into the occupied zone, and by the time it's dropped into the occupied zone, it's probably going to be the same temperature as your room air. And it will also work very well if you've got a VAV system and you need turn down. So we've got the same plaque diffuser, but now at a fraction of the air. We still get good pattern. It's still clinging to the ceiling, so it's not going to drop into the occupied zone too quickly. It's not going to create drafts. So this is going to be very good in cooling. So you're like, oh, perfect. I get to use my square plaque diffuser again, and it's going to work perfectly. But this is when we need to start thinking about what's going to happen when it's in heating. So when we look at the catalog performance, we're assuming isothermal throw. So isothermal throw would be the supply air temperature being the same as the room air temperature. If we have that diffuser in cooling or in heating instead, because that warm air is going to want to stick to the ceiling, we found that through testing and CFD and mock-ups that you can adjust the catalog throw 1% per degree Fahrenheit different from your room temperature. So you can look at your performance and adjust the throw, and you're always adjusting just that 50 feet per minute throw. When we're looking at cooling instead, that cold air is going to want to drop. So you're going to get some shorter throw. So again, you can use that same rule of thumb, horizontally 1% per degree Fahrenheit. And so you would look at our catalog performance and do that adjustment. And then you can do that throw mapping to again place your diffuser so that the 50 feet per minute throw in cooling and heating will ensure that people are comfortable. And really, this is the same in vertical. So vertically, you'd have isothermal throw in our catalog performance, but then when you're looking in heating, because the hot air doesn't want to go down into the occupied zone, you're going to get shorter throw. So you decrease the throw 1%, and in cooling, you would increase the throw by 1% per degree Fahrenheit. So that's a rule of thumb that we typically use. This is most likely used, or in most cases used, in perimeter applications, because that's where you're going to get heating and cooling. Ideally, and we've just seen this video, so I'll skip it for time purposes. Well, maybe not. So ideally, you would be able to have a slot diffuser, and that slot diffuser would do all of the conditioning from your perimeter zones. But in open offices like ours, where there are desks right against the window, that's just not going to be an option. So we're going to need to think of other solutions other than using a slot diffuser to condition your perimeter zone. So we just saw the SPD in full flow, and we saw that it got really good pattern. So what happens if we take that same SPD and now we derate the CFM, and we're now in heating instead? So the air coming out of the diffuser was at a slightly lower velocity, and we are seeing that, unlike in cooling, it's taking much longer to get into the occupied zone, and it's just grazing it. It's not coming all the way down to the floor. And if we rewind a little bit here, we can see what I was talking about. Some of that supply air is coming out, and then you can see there's a return grill here. It's kind of in the path of that air. The hot air is just basically going directly into the return. So if we had our return lower here, it would help a little bit because your primary air isn't going out. So what can we do if a square plaque diffuser is just not the solution for heating? So again, we've got the slot diffuser. Ideally, if you have an open office and you can, slot diffuser is going to be your best bet. So typically we'll recommend mounting it within 18 inches of a perimeter, and the air is going to go down, cling to the surface, and that's going to ensure that you're conditioning the window, and it's going to ensure that everybody is comfortable. The problem if you're mounting it 18 inches from a window is in cooling, probably because you're going to get longer throw. The throw is going to be too long, and you're going to be creating some ankle drafts. So here, what you would like, or what I would recommend doing instead, is installing the diffuser a little bit further away from your window. And then the air is going to hit the window or hit the wall and come down the window, and then condition the window without creating too many drafts. How can we make sure that that diffuser is going to work well in heating and cooling? Or how can we wash that window in heating and cooling? Because in heating, the hot air won't want to go down, and in cooling, we don't want it to go down too long. So we have come up with a solution that works well for most applications. So most ceiling heights of 9 to 10 feet, this window washing method will work well. So here we take those correction factors that we went over, so 1% per degree delta T, and we're looking at the throw and placing our diffuser so that in heating, the 50 feet per minute throw makes it 2/3 down the wall because it's going to keep moving. We're going to assume that because you've got regular ceiling heights, the air is going to keep moving down and condition that entire perimeter space. In cooling, we're going to, again, look at that 50 feet per minute throw, use the correction factor, and limit the throws 2 feet along the floor. So again, we're assuming that there's nobody against this window, and this is going to ensure that you're not going to get too many drafts for any occupants that are near the windows. This would be your ideal solution. But in most cases, like in our office, that was just not possible. So we need to think of other ideas that could also work. And that's when, again, those high induction diffusers are going to come in handy. So okay, I have enough time, I think. So let's go through a small example. We'll do the example, and then I'll hand it over to the other team. So if we've got a typical room, so here's a 20 by 20 room, but really you could take this room and multiply it by 6, 8, and you've got a large open office. So this is just for the sake of this demonstration. So we've got a room, we've got 9-foot ceilings, and we've got 1,000 CFM, and we know that we'll need about 4 diffusers. So typically they're going to be laid out so that they're all symmetrical. And so we're installing our diffusers 8 feet apart and 4 foot from a wall. So if we're thinking about the throw mapping again, we want the 50 feet per minute to be right above the occupied zone. And the occupied zone is 6 feet from any floor. So here the vertical distance that we would need to cover is 4 foot. So if we take the 4 foot horizontally that we saw in the last slide, and we add it to this vertical throw, ideally, we would need a diffuser that has 8 foot of throw, isothermal. So when we look at a diffuser that has 8 foot of throw, the first one that comes into mind will be our square plaque diffuser. So looking for something at 250 CFM, that's probably going to be a little bit too loud, a little too much pressure drop. So something with an 8-inch inlet is probably going to be good. But when we are looking at that performance, at that video, we know that that's probably not going to be it's going to work in cooling, but when we get to the heating, it's probably not going to mix well. So what other options do we have? Our next option would be a high induction diffuser. So that would be like a swirl diffuser, those hurricane diffusers, twist diffusers. These have very high induction rates. So it's going to mix the air in the room much faster than a square plaque diffuser would. So when we're looking at the performance, we're going to see it has a very similar performance than our square plaque diffuser. So we're still getting about 8 feet of throw, but because of the way that the diffuser, the air comes out of the diffuser, it's going to entrain a lot more of the room air, and it's going to ensure that it mixes quicker. So something like this is going to be very good in both heating and cooling because of those, because of the way that the diffuser is engineered. If we look at that radial slot diffuser, so here in the back, we've got our twist diffuser. So it has a radial pattern. The air is going to come out of in a twist. At that same 220 CFM in heating, we're going to see that the air does make it, we get a lot more mixing. So the air will make it into the room more quickly than the square plaque diffuser. The square plaque diffuser, the air did at the end get mixed, but it wasn't as quickly. So here we can see that the air really makes it all the way to the floor, and we're getting better entrainment with those high induction diffusers. So there's a few different ways that we could go about to validate our design. We could do a mock-up like we saw for the hospital room. We could do throw mapping, so we could place those diffusers, use those correction factors to make sure that we're placing our diffusers so that there's not going to be any drafts and people are going to be comfortable in heating and cooling. One method that gets thrown out there quite often is ADPI, so the Air Distribution Performance Index. That can be used. It works very well in cooling. ADPI basically has been designed so that you look at a diffuser and you look at the 50 feet per minute throw, and then you look at the distance the air has to travel, and you create a ratio. And ADPI, or ASHRAE with the ADPI table, has created a table where you can look at the ratio and see if that throw versus length is going to create a comfortable room. So they've tested a bunch of different diffusers. They put it in the ceiling. They tested like hundreds and hundreds of points to make sure that if you have this throw distance and this length, it's going to be comfortable. So it'll give you a rating up to 100. And typically we're trying to hit at least 80. This method is a lot of work. It can work well in cooling, but really in heating, it is lacking. So it was originally designed for cooling in mind. And in 2014, there was a research project to also add heating. The problem is in heating is you can get a very good score, but still not get good mixing. So you can get a very good score because your whole room is comfortable, but you have a lot of stratification. So ADPI can be used, but I would use it as a grain of with caution. And I mean, ADPI could be a whole presentation on its own, really. So I'll just stop it there. The last way we can kind of validate our design, and really this is going to be used in those critical spaces where comfort is really key, would be something like a CFD. That's going to be very good for really big rooms. A mock-up works well for small rooms, small offices, things that are easy for us to do in the lab. Something like an atrium or a school is a lot harder to mock up, and that's where CFD comes in handy. So here we had kind of the same idea of the throw mapping we just did. We have a classroom, and the idea here was that we need to condition this classroom and in heating and cooling with only diffusers. There were a few different iterations with radial diffusers and slot diffusers, and we ended up with 2 high induction diffusers. And just to kind of show that it really does work in both heating and cooling. So here we had our radial slot diffusers. And if we look at that CFD image, we really do see that swirl pattern. So it comes out, it swirls out, and then it hits either a wall or in another airflow pattern. And we can see that in heating, even though the supply air temperature of the diffuser was quite high, it was 87°F, because of that high induction, because you can see all of the room air getting pulled into it, we did end up with really good mixing and very low stratification. So it is a little bit colder at the ankle level, but compared to most other scenarios, we did end up with really good comfort. And sorry, I had to really go quickly through these one. Oh, we did have another question, and then I'll finish it up. The last question was, do you have any data on how roller or shade rollers, soffits, or bulkheads affect linear diffuser throw? Roller shades is a little bit tough. There's so many different roller shades out there. We have had mock-ups in the past where we basically have a slot diffuser and a shade, and it's like, how much CFM can I put it until the shade moves? Typically, it's not that much because you're throwing high velocity air against the roller shade. So that one is very hard, and there's just too many different configuration out there. Soffits or bulkheads, typically those can affect linear diffuser throw depending on where that linear diffuser is installed. So I do have some slides on bulkheads and how that affects throw. So after this presentation, let me put that together, and then Tom can send it out to the group, just because I don't want to take up too much of the other presenters' times. And just to summarize quickly, throw at the occupied zone, you want to get the 50 feet per minute throw right at the occupied zone to get the best comfort. In heating and cooling, you want to try to use high induction diffusers that have high velocities coming out to make sure that you have good mixing, and supply air temperature. The supply air temperature does have an effect on the performance, so make sure that this has been taken into consideration when installing or laying out your diffusers. And any final questions before I give the floor to our other presenter?
Any questions right now? Okay, we're good. Thank you very much. We're gonna take a 5 to 7 minute break. Let's be.
Okay, I'm in control again. All right, that's me. My name is Bob Klein. I'm a technical director with Price. I've been doing VAV diffusers for a while now. I've been in the industry for a while now. I stopped looking at numbers at this point. We are going to be talking about VAV diffusers. And really what I hope you get out of this is, one, what a VAV diffuser is, but two, we'll get a little bit of how the various types of VAV diffusers work. And then what I'm really going to focus on in the design section and really how to use VAV diffusers in your designs. So to get started, I'd like to just do a quick survey. And I'm not sure how this will work for those of you that are joining remote, but for those of you in the room, show of hands, how many of you have never heard of a VAV diffuser before? Hey, that's a good sign. Everyone's heard of one. Okay, how many of you heard of it but have never used one? A few hands there. Okay. Moving on down the scale then, how many of you used them on occasion, one or two here or there? Occasional hands there. And then how about toward the lower end of my scale here? How many of you have actually kind of laid out a project with them, laid out part of an area with them? A few nods. I don't see any real positive responses there. Really, our goal here is to get you comfortable with VAV diffusers and kind of move you down this scale and show you how you can use them as part of a design. I like to subtitle my presentation, How to Get Started Using VAV Diffusers to Enhance Your Designs. And really, when you design systems today, there's a lot of products on the market today. There's a lot of different ways you can design systems. These are all tools. I like to think of them as tools in your toolbox. And you've got a lot of different tools you can use, but a lot of us, we all have our favorite tool, and we tend to go to that tool a lot. Oh, I'm cut off again. Too many button pressing. Yeah, there we go. Everyone has their favorite tool. That's your go-to. You use it all the time. You're happy with it. You like it. But is it always the right tool for the job? And really, that's what we should be thinking about. You've got a lot of different ways to design systems, a lot of different tools in the toolbox. And are you using all of your tools? Yeah, you can make it work sometimes, right? But is it the right tool? So that's what I'd like to talk about today is VAV diffusers, where they fit into your toolbox, where you can use them. I'm going to start by explaining what a VAV diffuser is by talking about comfort. And that is our theme for our presentations this morning. I'll get into how a VAV diffuser works. And then, like I said, I'm going to really dive into these system examples to give you a feel for how to use them in your systems. So to get started, let's talk about what a VAV diffuser is. And to do that, I'm going to talk about comfort. But simply put, a VAV diffuser is a ceiling diffuser with an individual thermostat and a built-in VAV damper. So if you think about your traditional systems here, you've got a thermostat on a wall, you got a damper up in a duct. All we're doing is taking those devices and moving them into each diffuser. What does that do for your system design? Well, number one, each diffuser now has an individual thermostat. That means you can cater to individual preferences. You can create small zones of control, each with their own thermostat. Everybody gets their own set points. So when we talk about comfort, there's a lot of talk about, how do you achieve comfort in a space? What's the ASHRAE definition of comfort? It really is just a state of mind. That means you're never going to hit the right answer. But if you give everybody their own thermostat, you can at least get closer because at least they have their control, their own set point, their own control. By having small zone control individual thermostat, it also means, though, as loads shift around during the day, you're never biasing the load to the room with the thermostat because each room has a thermostat. So that's going to help prevent overcooling and overheating in your spaces by having these individual thermostats. So that's really the first part of this with a VAV diffuser, individual thermostats, individual control. The second part of a VAV diffuser is that built-in VAV damper. To talk about that, I'm going to do a little quick catch up on what we just heard about from a diffuser. And we are talking about ceiling systems. These are forced air ceiling systems. They are mixing systems. And as we heard in the previous presentation, they work by, number one, a good diffuser is going to start with a high discharge velocity of the supply air into the space. That high discharge velocity is important because, number one, it establishes the Coanda effect. Moving fluid sticks to a surface. Very important in cooling, so we don't have that cold air dumping down onto our occupants. Number two, that high discharge velocity also generates throw, the ability to move the air out and into the space. And then number three, that high discharge velocity also generates our entrainment forces, which draw room air up and into our supply air. So as these forces combine, the first thing we get occurring is mixing. These are mixing systems. Mixing is very important in cooling, but also very important in heating, because if we can mix that warm air, supply air with our room air, we're not trying to drive down such a high delta T. And all of this works together to establish this room air mixing pattern. That entrainment drawing the room air up to the supplier pushing it out around the room. As I say, these are forced air mixing systems. They achieve comfort by getting an even mix of air in the space. Now, when we design our systems, we design them for worst case scenarios. All the people in the room, all the sun load, all the loads in the space. And when you create your design, you've got to allow for this large volume of air that's going to meet your design loads. And when you have a large volume of air coming down a duct, you're going to get these nice high discharge velocities. Where a VAV diffuser is unique, though, is the location of that VAV damper and what happens on turn down as we reduce to lower volumes of air. By having a VAV damper built directly into the diffuser right at the discharge to the space, VAV diffusers maintain a near constant discharge velocity into the space. That means even at very low air volumes, you're getting a high discharge velocity. So these effects of good room air movement are still occurring. You're still maintaining coanda, you're still getting throws, you're still getting entrainment. All of that leads to good room air mixing. Again, not just at your design flows, but all the way down to your minimum flows. This can be demonstrated a variety of ways. This is a CFD, computational fluid dynamics analysis, looking at a VAV diffuser when it's 100% open, comparing it to when it's only 25% open. The colors there represent temperature, and you can see the even temperature distribution throughout the space. And that's showing that that good mixing is occurring. Providing even temperature distribution, again, not just at design airflow, all the way down to your minimum airflows. Another way to look at this was a test run using neutrally buoyant helium bubbles injected into the airstream to make air visible. Hit it with a bright light. That's those little streaks you see on the bubbles flying around. In this case, those three main photos, that's a VAV diffuser at 100%, 50%, and 25% open. Again, in each case, you're seeing that good discharge velocity, maintaining coanda, no air dumping, maintaining the throws, the entrainment forces bringing that air around, all of that leading to good room air mixing. And you can compare that to that little photo in the lower corner, which is kind of hidden by our menus there. But that's what a poor diffuser looks like. It's lost discharge velocity, coanda's been broken, and that cold air is just dumping onto the occupants. That's what we want to avoid. So by having that variable opening right at the discharge of the space, VAV diffusers maintain a near constant discharge velocity, and that leads to all these good room air movement. As I say, the coanda for no dumping, your throws, your entrainment, all of that leading to good room air mixing. So if we combine that, if we say a VAV diffuser provides you these individual thermostats, we bring in this good room air movement, what does that bring us? That leads to comfort. And it was mentioned earlier, comfort is really the primary reason we have air conditioning. And I know you have to worry about a lot of other things when you design your systems. You're worried about ventilation, you're worried about energy. But if it weren't for comfort, we wouldn't do any of this. So that should be one of your key design factors when you're designing your systems. So let's take a quick look at how VAV diffusers work. There are two primary types of VAV diffuser on the market today, and they're defined by the type of motor they use, and whether that's an electric motor or a thermal or mechanical motor. The mechanical diffusers, which are thermally powered, use these thermostatic actuators. Those are a copper bulb filled with a blend of petroleum distillate waxes. When the waxes get warm, they melt. That phase change produces a strong expansive force, drives a piston, and that acts as a motor for the diffuser. The other type of diffusers on the market are the digital or electric diffusers. Those use an electric motor, could be AC, DC, just depending on the different manufacturers in the market today. But that electric motor is used to drive the damper. So that's the differentiator between the two primary types of diffusers on the market today. The next thing a VAV diffuser needs is a supply air temperature sensor. The VAV diffusers do use the supply air temperature to determine whether the diffuser itself is in a heating or cooling mode. So they are measuring the supply air temperature to determine that. Cool air comes down the duct, puts the diffuser into a cooling mode. Warm air comes down the duct and puts the diffuser into a heating mode. We, of course, need to measure room temperature. Can't control room temperature unless you're measuring it. VAV diffusers will do that either with sensors built into the diffuser. And if they do have a sensor built into the diffuser, they're using an induction mechanism to draw room air into the diffuser. Actually provides a pretty good measurement of room temperature. If you remember that entrainment, bringing the room air under the diffuser, you're bringing a sample of that in. Or you can have a traditional wall thermostat and measure your room air temperature there. VAV damper, we have a VAV diffuser, we need a damper in there. Variety of different dampers on the market today. Could be a kind of blade type dampers, disc type dampers. There's even a model on the market today that has a sleeve type damper, but a variety of different ways you can then put a damper into the diffuser. And then lastly, a method to set the set point. Again, if you're working with those mechanical diffusers, set points are typically set up at the diffuser. If you do need, if you're working with the digital diffusers, it tends to be a wall thermostat, traditional push buttons on the wall. So those are your basic components to how a VAV diffuser works. Between the two, mechanical versus digital, when would you use one versus the other? Well, they're both providing these small zones of control, small zones of comfort. If you're just looking for a small zone of comfort, the mechanical ones do a very good job at that. And they have the advantages that they just lay in like a traditional diffuser. No wires, no power, no pneumatics. So you can create it, very easy to create a small zone of control. Creates a lot of options as far as easy to install, keeping costs down, retrofit opportunities. Where your digital electric diffusers come in is when you want to do more than just a small zone of control. So if you want to get into, say, occupancy sensing, work with CO2, tie it all back into a building automation system, that's when you'd switch over to a digital diffuser. All right, that's a really quick rundown on how they work. Now I'm going to move into some design examples. And, oh, question, go right ahead. So the question is, are VAV diffusers pressure independent? The answer there is most of them are not pressure. Most of the VAV diffusers are pressure dependent devices. They're being controlled by temperature. So when we had our little survey earlier, a lot of you said, I don't know, it was a lot of intermittent hand raising there, but a lot of times people's first introduction to a VAV diffuser is as a problem solver. You've had a system design, you've got a chronic complainer, you've got that one office that isn't quite hitting the temperatures you want to hit. Quite often a VAV diffuser just gets dropped in to solve a problem. And most of the time this works very well. And I say most of the time because this is where we're going to get into our little bit of design here. So VAV diffusers are modulating devices. They can close down to a minimum. And if you have a lot of them and they all close down to a minimum, you can build up pressure in your system. If the pressure goes up, the noise goes up, and we do not want noisy systems. So you do want to think about controlling the pressure in your system when you're working with a VAV diffuser. So let's talk about this problem solver where you've just dropped one in to solve a problem. Our first rule of thumb is our 30% rule. So if less than 30% of the total air volume is supplied through the VAV diffuser, then when they close to their minimums, you're not really going to get that pressure buildup in your system. There'll be a little buildup, but it'll be a negligible buildup. And so that's why as a problem solver, people have been able to just drop them in and kind of get away with it without thinking too hard. You're less than this 30% of your total air volume. So as we move through this, I'm going to start a little design section on the side there, our little design checklist. The number one check we want to think about is what are we going to do with pressure? And our first way of working with pressure is this 30% rule. As I say, less than 30%, you don't really need to worry about the pressure control. Now, that was all for a problem solver. But problem solver means we had a problem. We want to avoid problems. We want to be proactive in our designs. So you want to look for spaces that may be a problem in the future as you're doing your design and take care of them ahead of time. So in this case, I've shown a little example here where I've got a large open area, all served by the same system, but there's a couple of little private offices there. And maybe those private offices need a little more attention. They need a little more control. They're going to be a little bit different to the rest of that area. What do we do for those offices? Well, VAV diffuser is a great solution there. Our number one design check here is pressure. Because these are just two small rooms off of a larger space, we're going to be less than our 30% total air. We can drop a couple little VAV diffusers in, proactively take care of any potential issues, give those offices a little bit of independent control. Let's say we have a row of private offices though, and we'd like to give everyone their own thermostat. You'd say, probably everyone here would say, I'd love to give everyone their own thermostat, but it just costs too much, right? Let's talk a little bit about cost. cost really breaks down to is what is the cost of a zone of control? You can design a very inexpensive system by creating large zones. So in the top there, I've got a ratio of 8 diffusers per thermostat. So a big zone system, it's going to be inexpensive because you got minimal controls. So if you're looking to keep your costs down, that's a way to do it. But maybe that control's not good enough. We look in the center there. I've dropped the ratio to 4 diffusers per thermostat. Smaller zones of control. Our control is getting better, but our costs are increasing. At the bottom there, I've dropped it to 2 diffusers per thermostat. Now our control is getting really good. We got a lot of small zones, but our cost is really going up. If you bring in a VAV diffuser system, cost-wise, typically they about break even with that center area, about that 4-to-1 ratio. So if you've got about 4 diffusers per thermostat, and this is on an installed cost basis when you're looking at the total system. A lot of folks get the idea, oh, VAV diffusers are expensive. And certainly if you compare a VAV diffuser to just a square plaque diffuser, they're going to appear very expensive. What you need to look at though is the system, because they are a control device. You are getting more than just the diffuser. And when you compare it on a system basis, on a full install cost basis, they can become very economical when you're looking at small zone control. Again, cost-wise about break even at 4-to-1, but you're getting individual room zone control. So a thermostat per room. So let's go back to our example here. We have a row of private offices. We'd like to give everybody their own thermostat. Cost-wise, we think we can do it. Hopefully, you're all now starting to think VAV diffusers here is our solution. Our number one check here as far as system design is pressure. Now we've got a whole row of offices here. We're going to be over this 30% rule. So what's our next approach? Well, we can come in with a modulating zone damper. So we can create a pressure zone around the diffusers just by putting a damper up in the duct, controlling it to static pressure. Do we have a question? Oh, okay. Question came in, are there any comments regarding the 30% rule pertaining specifically to a constant volume system? Presumably a VAV system would have a, wait a second, differential pressure temperature, which would decrease supply fan speed in response to higher supply duct pressure. So I will address a constant volume system coming up here, but in general, that 30% rule can be applied to a constant volume system. What we're really saying there is, if you're less than 30% of your total air volume, when that diffuser closes to a minimum, you're not going to increase the pressure in your system. And that's whether it's a constant volume fan or if you had a variable volume fan, what you're going to see is you're not going to see a pressure change in the system, minimal change. So even if it was a variable volume fan, it wouldn't really adjust or it wouldn't need to adjust because you haven't really influenced the pressure. So that's true for constant volume fan or variable volume. If you're less than the 30%, it may not even see it. But if you're more, then yes. And I'll touch on that coming up here. So in this case, we're saying we've got a row of private offices. We want to give everyone their own thermostat. How do we control pressure? Well, one way to do that is with a modulating zone damper, create a low pressure zone around amongst the diffusers. Static pressure sensor located 2/3, halfway down the duct. Back to control that damper. So now as our diffusers close up, that damper can close up with them. As our diffusers open up, our damper opens up with them. Again, if you had a variable speed drive on your fan, you can run that upstream of that just like you would with any VAV system, monitor the pressure in your higher pressure areas of your duct and use that to control your fan speed. Moving along here. Just another example. So here's another little row of private offices. How do we give everyone their own thermostat? Hopefully you're all answering VAV diffusers now. In this case, though, I've got a little dedicated unit controlling that perimeter space. So dedicated unit, relatively short duct runs. This is in a scenario where you could do direct fan speed control. So now instead of having that modulating damper, we're going to put the static pressure sensor amongst the diffusers, again, 1/2, 2/3 down the duct, but now direct back to our fan speed control. So as our diffusers close up, slow down the fan. As our diffusers open up, speed up the fan. Let me say, just checking my next slide there. We've got a perimeter zone now. You're thinking, hey, I'm taking care of my pressure, but let's talk a little bit about heat. What are we going to do about heat in this scenario? Well, a VAV diffuser is kind of true to the definition of VAV. They are varying the air volume to control the temperature in the space. What does that really mean? It means that you don't want to also be trying to vary the supply air temperature to control the temperature in the space, because you'll have the two kind of fighting each other. So VAV diffusers do work best when you have a consistent supply air temperature. Not saying you can't change your supply air temperature. You certainly can. You can run supply air temperature reset strategies, but you want to maintain a more consistent supply air temperature. A step type of an approach works well, where you hold a temperature for a while, decide to make a change, make that change, hold the new temperature for a while. If any of you all are really into controls, latest trend in controls has been trim and respond. Trim and respond does make frequent changes, but it also makes very small changes. The result there is a slowly changing temperature. So a trim and respond approach can also work well as part of your supply air temperature reset strategy. The other part of this is, I mentioned earlier, the VAV diffusers are sensing the supply air temperature to determine their independent heating cooling modes. That means we do need something to tell the system when to switch between heating and cooling. So that's something else we need to design into our systems. Oh, you've cut me off again with that little maneuver. There we go. So let's go back to our example here. Row of private offices, dedicated unit. Pressure-wise, we're going to control it using the direct fan speed control, and I've expanded our little design checklist there again. We now thinking, in addition to pressure control, let's think about our supply air temperature control, get that consistency, get that control in. How would we work with a system like this? Well, you can put a discharge air temperature sensor on your unit. That way you get a consistent temperature. If we're measuring our discharge air temperature, we can control the unit using that. And then pick a representative room, put a thermostat in that representative room, and have that tell the unit when to switch between heating and cooling modes. Then allow the diffusers to create those small zones of control within that and control the individual spaces. This approach with a dedicated unit, direct fan speed control, can be a very energy efficient approach. I say that because we're really minimizing or eliminating all the unnecessary pressure drops in your system. So you're running the entire system at low pressure. Very effective, as I say, keeping your energy down, providing good comfort control within the space. And then by using a dedicated unit, you're also avoiding the need for reheat. If you've zoned your building with dedicated units, like say, if I've got one controlling that perimeter, the unit itself switches between heating and cooling. We're not using reheat energy to heat those perimeters. Let me move along to another example. Here I've got, again, another little row of private offices. How do we give everyone their own thermostat? There we go. We got somebody listening this morning. The nice thing here is this could be a traditional VAV box layout where you're using VAV boxes in your larger open spaces. When you hit those small private offices, bring in the VAV diffusers. Again, let's run our design checks. I got to do my pressure control. I'm looking at my supply air temperature control. Well, a VAV box is a great package to provide both of those. VAV box has a damper on the inlet. It's pretty easy to convert a pressure independent VAV box to a pressure controller. So that can provide your pressure control, create your zone of low pressure amongst the diffusers. But number 2 of the VAV boxes has a coil. So it's a great source of, I'd say, a nice package with damper and coil. We've now got our source of heat. Put a discharge air temperature sensor off the box, let it control the coil. Thermostat, representative room, that tells the box when to bring the coil on, when to bring it off again. VAV diffusers providing those small zones of control within the individual spaces. Again, it's all about these tools in the toolbox, picking the right tool for the job. And again, this is all leading to better comfort because you're using the right tool for the job. So, sorry, that was the example we were just looking at. Question came up earlier, what about a constant volume unit? So here's a little system, constant volume unit, little package rooftop, DX rooftop, whatever it might be. I've got a portion of a building here with a bunch of small spaces. Hopefully you're all thinking VAV diffusers. I'm gonna run my design checks, pressure control. What do we do for pressure control? Well, constant volume means we have to run some kind of a bypass. So earlier we mentioned 30% rule. If you're below 30%, you can drop a diffuser in without too much worry. If you're above 30% though, you're gonna need a bypass. Bypass could be, as I've shown in the drawing here, it could be a little duct between the supply and the return with a modulating damper to control that. VAV diffusers, there are options to even have a little bypass local to the inlet of the diffuser. So you have a variety of options with how you design your bypass. In this case, modulating damper, static pressure sensor, 1/2 to 2/3 down the duct, controlling that modulating damper. A little bit different before though, as our diffusers open, the bypass closes. As our diffusers close, the bypass open, keeps the air moving through the system. You don't have to slow the fan down because you can't. Keeps the air moving over the coil. The difference here a little bit is, ideally, if you can do discharge air temperature control, that's great. But if we're talking about a constant volume unit, it's probably a less sophisticated unit. You may only have 2 stages of cooling, 2 stages of heating. At a minimum, you want to get a discharge air or a duct mounted thermostat on the discharge to that unit. And the reason for that duct mounted thermostat is if we're bypassing a lot of cold air, we don't want to freeze the coil. So that adds a little bit of protection in the unit. As that supply air temperature starts getting too cold, we can cut off the compressor. As it warms up again, bring the compressor back on. So that provides that little bit of extra protection to the unit. Switching between heating and cooling, again, you can go with a representative room, thermostat in a representative room, use that to switch your coil on and off. Last part of our design guidelines here are zoning. So VAV diffusers are not an answer to poor zoning. You still need good zoning in your building. And I've used the word zoning a lot. We have pressure zones. This is thermal zones. So this is separating your perimeters from your interior, making sure we can heat in the north while we're still cooling in the south. So if we take that into adding that, again, design checklist, that's our 3rd design check on there. What is our zoning? Here's another example. I've got a large perimeter. I've got some interior. We're going to put them on separate sources of heat so that we can heat or cool that perimeter while we're doing the opposite to the interior if we need to. Running through the full checklist here, the zoning looks good because we've separated it out. Comes to pressure control, we're greater than 30% in this case, lots of small rooms. So we're going to use a modulating zone damper. And then when it comes to that supply air temperature, how are we creating that heat? We can use a reheat coil. And I think this project was actually broken into 2. There's a split right about there. So that kind of southern portion of the perimeter is on 1 reheat coil. The northern portion of the perimeter is on a 2nd reheat coil. Interior is on its own reheat coil. That's creating our zoning for us. Again, discharge air temperature sensor off that source of reheat so we can control the reheat. Thermostat in a representative room to tell the unit when to switch or the coil when to switch on, when to switch off. Just another example here, again, this time using dedicated units. And these could be small rooftops, it could be heat pumps, it could be fan coils. Any little unit that's going to give you the ability to heat and cool. But by creating your thermal zoning, again, separating your perimeter from your interior by using a dedicated unit, you don't need reheat. So again, if you're thinking energy, if you're thinking efficiency, this is a great approach because you're avoiding the need for reheat. You create your thermal zoning using dedicated units. Similar to our design, running down our design checks, pressure control. We've got a smaller area, we've got a direct unit, so Could be a good opportunity for direct fan speed control on our pressure control. Zoning looks good because we've split it out using the 2 units. And then when it comes to the supply air temperature, discharge air temperature sensor on the unit, control the temperature of the air, thermostat, representative room to tell the unit when to switch between cooling and heating. This dedicated unit approach isn't just limited to small areas. You can look at larger spaces. This particular building had rows of private offices all on one face of the building. I show 2 stories here. So if we have a dedicated unit, say on that northern exposure, no need for reheat, have that whole face of the building kind of working in a similar load profile. Again, like usage, like exposure, and using the VAV diffuser to create those small zones of control within it. Pressure-wise, use a modulating damper on each floor of the building to create that low pressure zone on each floor. Move the air up and down the risers using a little bit higher pressure. When it comes to that supply air temperature control, discharge air temperature sensor on our unit to control that supply air temperature. And I've been using a representative thermostat in a representative room a lot in these examples. I pulled this example in. This is a much larger area. Maybe that one representative room is kind of hard to find. What's your options there? Well, certainly there's a lot of thermostats on the market today that use remote sensors, so you could pick up more than one room. Or this is where your digital diffusers come in. If we're working with digital diffusers, you can tie them back to your building automation system, run a voting sequence, use that voting sequence to drive a supplier temperature reset strategy. I've seen a lot of projects too where they're not all digital diffusers. They just dot in a couple where they want critical zones to take measurements, use the mechanical ones everywhere else. That's a good way to keep budget under control. And this leads me into my final example. I've shown you a lot of partial systems. Like I say, you can work them into your designs quite easily, but you can also do a whole building this way. I don't want you to discourage that, but certainly you want to, if you've never used them before, get started with a couple here and there and see how they work for you. But full building design has been done. This was a medical office building, so not a hospital, medical office building, no overnight stay, but a lot of small zone requirement. Doctor's offices, exam rooms, great application for VAV diffusers. This particular building, 8 stories tall, double lead platinum. Is lead, anyone, you guys do a lot of lead here? Any interest in lead? So, maybe. I like lead because, at least from my point of view in presentations, it gives me some qualifications for what we're talking about, right? Somebody actually measured this and checked it, just not me showing you pictures the whole time. This particular building, double lead platinum, they got platinum on the core and shell, and they came back and got a platinum on the interiors. VAV diffusers throughout the building, over 1,000 VAV diffusers in this building. What's interesting about it is they were half and half mechanical and digital. So they decided to put the digital diffusers in what they deem their critical spaces to collect data, that being doctors' offices, exam rooms. They used the mechanical diffusers in the less critical spaces, still needed comfort, just deemed less critical, hallways, waiting rooms. By the colors on there, if they're coming through, anything in blue is a digital diffuser, anything in green is a mechanical diffuser. So this big area here was a waiting room, and you can see a lot of little exam rooms, doctors' offices in that area. Other than that, it's a pretty traditional reheat type of an approach. If you're thinking about your traditional VAV box system where you'd create a zone and reheat it, all that's been done here are these larger zones, like usage, like exposure, sub-zoned with the VAV diffusers. So a couple of big air handlers on this building, moving air throughout the building using some higher pressure. Again, if we run our design checks, we're going to drop to lower pressure in each zone by using a modulating damper, create low pressure zone amongst our diffusers. Reheat coil per zone as well as our source of heat, as well as creating our thermal zoning within the building. And in this case, digital diffusers providing votes on when to switch between cooling and heating, or even to drive that supplier temperature reset strategy. Question?
You mentioned, using some digital, some mechanical for cost savings. Like, how much of a cost saving difference is there between the two?
So the question coming in is, what's the cost difference between mechanical and digital diffusers? And again, in general, a digital diffuser probably runs 50 to 100% more than a mechanical, just depending on the amount of features you're getting with it. The thing to keep in mind though is when you go digital diffusers, typically you're tying them back into a building automation system. The building automation costs can well outweigh the cost of the diffusers. So there is a cost to get a fully automated building. Please. Yes, so question is what other, I'll summarize the question really, what other data or information is available from a digital VAV diffuser once you've got it tied into a building automation system? Most of the diffusers have a lot of data available. They'll be telling you supply air temperature, room temperature, set point, damper position. There's diffusers on the market that measure the flow out of each diffuser. You'll get into a variety of different commands you can issue, override commands, force them open, force them closed. As I said, you can get into other operations as well, occupancy sensing, CO2 sensing, and that information will be fed back to your building automation system as well. So a lot of, like having any other fully automated device, it collects a lot of data. Most buildings don't use it all, but there's a lot available depending on what you need to operate your particular building. So, yes, so this presentation's been a little bit generic on VAV diffusers in general. Different manufacturers, and I can say we're coming, that was actually my last slide, so I can pretend I only do that because if you're going for your continuing education credits, we keep it brandless. But if we're calling it the end here, we can talk a little bit brand specific. At Price, we offer a whole variety of shapes and sizes of VAV diffusers. It's not just the square plaque style, which I think most people have seen. We do have linear slots, both ceiling and sidewall. They can even go continuous look where you create those long slots that go on forever that the architects really like. We have them round. We have them big and small. We even have a swirl-faced one, if anyone was teased by that swirl part in the previous presentation. Certainly our experience is North America doesn't really care about swirls, but Europe likes them. And for us, Australia really likes them. Not because they work better, they just like the look of them. So whole variety of shapes and sizes you can work with. All right, just moving through this then, that was comfort from VAV diffusers. Comfort provided by small zones with individual thermostats and that built-in VAV damper providing those constant air velocities, which lead to that good room air movement. We broke down how the diffusers worked and then concluded with those design examples. And like I say, I keep showing my toolbox here. I'm really hoping that you'll take away from this that this is yet another tool in your toolbox that you should be making use of. And as long as you follow our design checks, make sure you've done something to check your pressure. And if you need pressure control, put something in the system to control that pressure. And then 2, look at how you're controlling your supply air temperature. And number 3, make sure you've got good thermal zoning. You should have a great system, and it's going to provide that additional level of comfort through those small zones of control. All right, any other questions? You've been a very quiet crowd. I don't see any from the online. Oh, there we go, question. So the question coming in is wiring. If we have to wire our diffusers back to the, I'm thinking you're saying like a VAV box? Yeah, so if you have a VAV box and you're subzoning with VAV diffusers, you have to wire it all back. Essentially, no. You could do that scenario with mechanical diffusers. The control between the two isn't direct, it's indirect, meaning we want that VAV box to provide pressure control. It's going to do that by measuring the pressure. So it doesn't actually have to talk to the diffusers. It just needs that pressure sensor to control the pressure. Similar on the supply air temperature. It needs to know when to switch between heating and cooling. Could you get that from the diffusers? Yes, if you have a digital diffuser. Does it have to come from the diffuser? No. You could have a thermostat representative room just to provide that data. Any other questions? No? Very quiet. I didn't give out a single ticket. Oh yeah, we've had some questions. I get some tickets. The real question is, when do you use a VAV diffuser? I like that. You get 2 tickets. Yeah. Well, I only got a few tickets. Ticket. Who else asked some questions? I believe you asked a question. There you go, sir. All right, how are we doing on time?
All right. Well, good morning, everyone. I'm going to get started with the displacement ventilation presentation. So just to introduce myself a little bit, my name is Narayan Sridhar. I'm from the Winnipeg office for Price Manufacturing. So kind of started with the design team and operations. Actually, very recently, well, in the last year and a bit, I've been with actually Bob here as part of the VAV diffuser team, but only in the last couple months back with displacement. So hopefully we can cover a good amount of your questions and just kind of in general do an overview of displacement systems. So displacement is one of a larger umbrella of products at Price and includes chilled beams, displacement, radiant, underfloor, and of course VAV diffusers. So all your kind of niche systems, not your typical commodity GRD products and air moving products. So in this presentation, I'm just going to focus on displacement. I'm going to do about a 25-ish minute, really quick run through, some high level stuff, and I'm going to actually switch over to Mike Kuprianov, who's going to join us virtually to speak specifically to CFD and how that's really applicable in a system like this. Really focusing on comfort. So yeah, we'll go through overview and benefits, common applications, design considerations, and design support. So I just want to kind of quickly compare traditional systems, mixing systems to displacement ventilation. Sandrine, Bob kind of covered typical mixing systems. This is just another type of system overall. So on the left is a mixing situation, and then on the right is a displacement here. So when we focus on a traditional mixing system, usually that air is delivered at higher velocities at 55 degrees, really driving that air motion. So the diffuser itself is what drives that air motion. With a system like this, there is a potential for pollutants and contaminants within your space. So the idea here is we are really focusing on the entire space and really a uniform system to cater to that entire zone. This is a little different than a displacement system. So displacement, underfloor systems, both are kind of stratified. Stratified meaning kind of layering of air. So really just focusing on the tailored zone. So in this case, we're delivering air at lower velocity, and higher supply air temperatures around that 65-degree air. So this is a little bit different in the sense that we're focusing on the breathing zone or the occupied zone. So that's kind of what we determine as 1 foot off the walls and 6 foot off the floor. Really just catering to the occupants within that space and just really tying into the comfort aspect. So in this 65-degree air, essentially what that equates to is higher energy savings associated with this, and you're really pushing contaminants up and away from that breathing zone and higher up in your space to your return. So this is a quick video showcasing how that works. So this is simulating some heat sources and displacement diffuser in the corner. You can see the smoke pattern go, and it's naturally finding its heat sources. This is different than a mixing system in the sense that the diffuser itself isn't what's driving air motion. It's the thermal plumes given off of the heat loads. So occupants within a space, lighting, equipment, things like that, we're giving off a convective load. And that thermal plume that's generated is essentially what's conditioning your space. So you're delivering fresh air at low levels or around low levels, and the heat sources in the room are what drives that air motion, and using buoyancy forces naturally, that's what conditions the space overall. So hopefully that makes sense. So the overview of like a system like this is really, there's a variety of benefits. The major ones to focus on here is really the flexibility, energy savings, and indoor air quality. This system, as you can see in that video, is finding its heat sources, so it's super flexible. However, it does matter where exactly it's placed. For example, we'll kind of cover some examples, but we don't really necessarily want to place it like right behind a bookshelf or something like that. It is very adaptable within your spaces and finds its heat sources, but that makes it very flexible in a variety of different applications. And from an energy savings perspective, that fresh air is delivered at 65 degrees and finds its way to the occupants in the space, a little different than that overhead mixing at 55 degrees. So you lower rooftop air handlers and things like that, a lot of improvement. And the whole key here is to focus on indoor air quality, really trying to improve that ventilation effectiveness and push those contaminants up and away from that breathing zone. So with a system like this, because you're delivering air at that 65 degrees, really making use of your economizer and maximizing that longer throughout the season is essentially what this is trying to showcase. So that higher supplier temperature allows you to have more free cooling hours of your economizer. So air quality, this is probably the #1 major benefit outside of the obvious comfort with displacement ventilation. So again, we kind of spoke about like the pollutants and the potential for contaminants to be out of that breathing zone. And so that's what that E sub Z is here. This is the ventilation effectiveness. So this is really just a measure of how many, what's the concentration of contaminants in my return zone relative to the concentration of contaminants in my occupied zone. So I want that to be as high as possible. With a mixing system, obviously it's a uniform unity value. We're mixing that entire space. So it's around that 1.0. With displacement, we're using those thermal plumes and delivering that fresh air at low levels. And that convective load is what's conditioning the space. And so that's where you have the higher potential of contaminants up in the return zone. So this really just equates to a higher amount of energy savings because you don't need as much ventilation or outdoor air according to the ASHRAE 55 standards to deliver that same amount of air. And we'll kind of look at that a little bit more. So schools have been like the primary driver of displacement that we've seen in the market that I'm in Winnipeg and Alberta and things like that in Canada. We've really seen displacement take off in the school division, primarily for the indoor air quality benefits. So this is just to kind of showcase like there's a lot of schools already using it and they've seen a lot of success with it, a lot of indoor air quality studies. We've done our own studies at Price kind of showcasing displacement and it's been hugely beneficial. We've also done some technical writing as well and publications of this kind of system. So last year, a year ago now, December 22, we did a technical feature in the ASHRAE journal showcasing displacement ventilation actually being beneficial for particulate controls and contaminants in a space and airborne pathogens. So we did that setup right in Winnipeg. There's also another one that we did, Sustainable Cities and Society. So this is all accessible if you're curious. The study in Winnipeg is a little image here showcasing our setup. Shows the airborne pathogens essentially set up here. And what really this is showcasing is that even with reduced, increased air changes per hour, you're still, whether it's a mixing system or displacement, still reducing the overall number of particulates in the space. With displacement, there's a higher potential and energy savings on top of that. So I won't spend too much time on this in particular, but there's a lot of different publications and studies already showcasing this. This is just an example of one of our own that we did, showcasing the improvement from an energy point of view and indoor air quality with displacement. So this is another snapshot of actually a CFD analysis of that same setup, showcasing a mixing ventilation versus a displacement ventilation for a seated and standing occupant of that same particle study. And you can see just from the images here and stuff, no, they're not on fire. They're just a simulation of it. But it's showcasing basically the air quality being improved by pushing those contaminants up and away from that breathing zone. So I won't spend too much time talking about this because it doesn't sound like LEED is that big of a deal. But in general, a system like this is very beneficial for systems like LEED and CHIPS and wells and things like that, dedicated to different applications, where you can actually get awarded a lot of points by using a sustainable system. So some applications, I mentioned the education division, like that is essentially the largest driver of the market. So this is an image from Odyssey Elementary School. In the back by the teacher's desk there, you can see that displacement diffuser built right into the wall. That's a perfect example of where you'd see displacement typically used. In this space, you can see the tables, they all have wheels. There's the kids moving around, the tables moving around all the time. Having a displacement diffuser just wash out and naturally find its heat sources is super useful, especially when there's not a lot of space on the walls and things like that, cubbies and lockers and things like that in the space. So very easy to integrate within your space, very easy to condition your space, and just be incorporated in a modular, flexible environment. Libraries, so that higher supplier temperatures, lower velocities really make it beneficial for in spaces where sound is of importance, much like auditoriums and things like that. Libraries are another key one. So here we have round floor. Technically, this is an underfloor system, but it's still a displacement pattern of air delivery. So the round floor diffuses right at occupant levels within your space. So airports, a lot of people moving around, a lot of potential for contaminants kind of going throughout your space. And more, we're seeing a lot of different displacement products incorporated into the architecture of the space. So you can see here, just on the seated portions, just on the base around the base there, there's like incorporated right into the architecture of the space. So really seeing it all the time now, hidden away in all sorts of applications for airports. And so I mentioned auditoriums. You know, if you think about a mixing system here, the ceilings need to be high. We need to dissipate sound. A lot of occupants sitting close together, a lot of heat sources all together coming in at once. This would be a lot of cost possibly from a mixing system. So having a displacement system where you can have air essentially being delivered right at occupant levels or on the stage or on the stair risers or things like that, naturally finding its heat sources and conditioning, you save a lot of energy there. And again, that higher supplier temperature, lower velocity makes it really susceptible or really beneficial, advantageous from a sound perspective. Industrial applications. So this is really the birthplace of displacement and stratified systems. Europe started using displacement ventilation by providing fresh air at occupant levels for production workers and pushing all those contaminants away. And then along the way, North America was like, why aren't we doing this, basically? So much like everything else, we take a lot from Europe. And this is a great example of where this has started and kind of taken off. And so again, another example, this is San Francisco Airport on the right, and on the left, this is the Edmonton International Airport. So for Price, I would say about 80% to 85% of what we do is special for displacement, custom perf, custom finish, custom sizes, and things like that. And that's essentially what's very common for displacement. It really needs to fit into your architectural needs and kind of be flexible within your environment. So this is just an example of how it's really fit into those architectural needs and just hidden away in various amount of spaces. So this is a image of our Winnipeg facility, our cafe area, where we recently redid it with a bunch of different displacement diffusers. So the planter boxes themselves are displacement diffusers. On the walls, the columns and stuff, they're all displacement diffusers as well. Really easy to incorporate within your space to be flexible and be close enough right near occupants so they don't create any drafts or anything like that, really tailoring towards that comfort. So I'll speak on some design considerations. I just want to throw a shout out to this handbook. This is the old image. We have the new one. I know, Caleb, you got some samples here of the new handbook. Really useful tool. We spent a lot of time on really honing in on all the different types of systems, much like displacement and VAV diffusers and GRD and things like that. So useful tool to help calculate a lot of the loads and how to design your spaces. So when I kind of mentioned like air volume calculations and kind of tailoring to the breathing zone, this is clearly a perfect example of what I'm trying to say. This is just tailoring exactly to that occupied zone. So what, 1 foot off the walls and 6 foot off the floor is essentially the load to calculate in a system like that. When it comes to calculating your loads, we're not really changing anything compared to typical. You're still calculating the overall load you need, but you know, whether it's overhead lighting, your solar loads, as well as your occupants and equipment. But when it comes to displacement, what ASHRAE is essentially the message behind it is you're only taking a portion of that load into consideration when you're occupied space. So for example, your overhead lighting, it's really just the radiative component of it. So it's 13.2% of that load. This is all from ASHRAE 55. And so that's just where these loads are calculated from. So you plug in all this into essentially an equation like this to calculate your outdoor air requirements for this. The delta T on the bottom, and I know I'm going over this fast, I can share slides and stuff after, but is essentially your stratification temperature. So for a seated occupant, that's 5.4 degrees between head and ankle height. And for a standing occupant, that's the 7.2 degrees. So we don't want any heads that are warm and toes that are cold. We want to limit our stratification there. So this is just showcasing from ASHRAE 55 that change in differential and that stratification. So duct sizing here, the whole idea behind displacement is, especially from a low wall perspective, we're trying to create a face velocity around that 40 to 50 feet per minute face velocity. So we're really limiting our inlets to around that 1,000 feet per minute and just maximizing on that face velocity to get that nice flow of air like you saw in that video. From a heating perspective, we want to be careful by not short circuiting when using displacement for heating. So on the far right here, that's the aspect of short circuiting when we're beyond that 5-degree differential from supply. So usually around that isothermal 2-5-degree temperature range is enough for that horizontal pattern of airflow comparative to the cooling. So when it comes to heating, a lot of different options that we typically see are radiant panels mixed in with displacement, chilled beams as a baseboard type cabinet, drop-in ceiling style for overhead. This is all examples of how you can incorporate heating options right in your applications with displacement. Sorry? E-strat. Yeah, yeah.
Got everything there. Well, you can go, well, you can't use it, so I'm not gonna use displacement. You can get around. It's not that. Some air barriers or help even help. You're gonna use it for what, 15 minutes a day, and then you're done for the day if it's highly occupied space. So people, I hear it all the, well, you can't heat with it, so I can't use it. No, you can do it.
No worries. Yeah. So I'll kind of cover very quickly some of our different products here. I don't want to spend too much time on this stuff, but basically with displacement, the whole idea that I'm trying to showcase is there's a variety of different options. It's a very flexible system and really tailored to that occupied space. So it needs to be, really stretch and pull to fit within your architectural needs. And that's what this is showcasing. So whether it's wall mounted, floor mounted, heat cool, overhead, even displacement, it still essentially works that same way, even if it's overhead. It's finding its way towards the heat sources, and the heat sources itself is what drives that air motion. So this is just some very common displacement diffusers that we typically see. So the DFR, for example, that's like the one that's like on the stair risers or around that seated area in the airports that we saw. And then a lot of round style diffusers as well that's kind of incorporated. From a floor point of view, that MFD, that's a raised access floor. That's an underfloor type of system that we saw in that library example. And so that's the type of diffuser there. Even for auditoriums and things like that, that's the DFGL. Curved or linear, discrete, continuous, all of these kinds of options exist. And we commonly see that for displacement applications. There's some quick examples of these floor mounted styles and ceiling examples. So this is one where we have a heat cool changeover. So this guy right here. So we have a full plenum face that's delivering that cooling mode, and then it changes over to the actuator. The actuator changes over, to a channel, and that's essentially the heating mode there. So a couple different options. It's an example of where you typically see those in a lunchroom or a cafeteria or an office space. So as I mentioned, a lot of this needs to be customizable. So, custom perf sizes, all of that, it really needs to incorporate within your space. And that's something that we're very used to doing. We've done even projects where, you have column wrapped diffusers that are displacement and they have hinged doors. So all your electrical cable work is right inside. Very adaptable within your space. And that's the real kicker with displacement. It's architecturally friendly and adaptable. Yeah. So I think it depends on the convective load of it. Like, for example, the ones like this DLEH and things like that isn't as prominent of a convective load to compete where it's pulling all that supply air out. So it is typically decoupled depending on the type of displacement you're using. So we don't want it too close where we are short circuiting and things like that. And that's where our team can help lay out exactly where the placement of the diffusers and things like that. Because although it is flexible, we don't want it to essentially limit how it flows within a space. Yeah. Exactly, yeah. So that's one where you'd put more on like an inside wall or something like that, where it can be still close to an occupant, but they're not experiencing an intense draft or anything like that, yeah. So just some more examples. So on the left here, this is an example, not the best quality picture, but still a good example of where displacement's kind of used in a cafeteria, where it's kind of really incorporated right into like the tabletops and things like that. And this is one where it has the custom hinge doors that I mentioned as well. So auditoriums, like Kaufman Theater, this is a great example. Like I mentioned, a lot of people sitting close together. Here, every second seat has a raised platform, a round floor diffuser for every seat. The stairways and the stage sides areas and things like that, they're all using displacement hidden around. Even the lobby area is using curved displacement throughout. So easy to incorporate, high ceilings, a lot of people, really tailoring towards that comfort need that exists in a space like this. So this is just a couple views of like the analysis that went through for the Kaufman Theater, and we really worked with Mike, who's going to be speaking here soon, on the CFD side, incorporated really how to showcase and tailor the space exactly for thermal comfort when it came to displacement, and a lot of effective use using a system like this compared to mixing systems. So from a selection point of view, really just selecting the round floor baskets or round floor diffuser, sorry, for one that doesn't really involve any sound issues and things like that. That was part of the aspect of it as well. Sorry, I'm going fast just because I want to make sure give Mike an opportunity to speak on CFD as well. So this is just showcasing the same thing, why overhead is really beneficial. Spaces in spaces where space is limited, I guess. That'd be a great application where displacement overhead is still used. So this is just showcasing a smoke video of that same idea. So here you can see the cooling mode where it's just falling right to the floor and finding its heat sources. So that's that cooling mode there. And I don't have the heating one. We had a little bit of an issue with that, but I can send that over post. So this is a great overview of essentially where you'd use them. So overhead is really ideal for, again, that spaces where you're limited on floor space. However, it's a little bit more flexible with a sidewall, again, where it finds its heat sources. When it comes to overhead, putting it right above an occupant or an inside wall and things like that, location would matter a little bit more from an overhead perspective, but still works just as well. So some more examples of displacement diffusers throughout. I'll skip over this. This one was an interesting one here for an office space. This is a Google project where they had a larger space and they wanted a bunch of displacement diffusers in series. So this was an interesting one for me when we were testing this, where we had large, so these diffusers here are about 4 foot diameter. They're massive. And they have, what we did is horizontal perf right inside at varying lengths to essentially make sure that we're conditioning that space effectively throughout. So you're getting that nice flow of air as this whole space. This is more of like an expo, larger atrium type space. And so this is just a quick video of like us testing this. So a lot of occupants seated together. This is the kind of stuff that we do all the time in Winnipeg in our lab. Just showcasing how we tested those series displacement diffusers together. Yeah, so really just showcasing the effect of a wall, how it would work, and kind of mocking that up when you have that much heat load. Something that's important to note as well is that the heat load is, as the heat load regulates, you're still tailoring towards that thermal comfort. So if you have like different ranges in metabolic rate and different heat sources, you're still tailoring to that comfort in stages. So yeah, just want to showcase that. I won't spend too much time in DV and healthcare. I'll say overall, we still see it a lot of applications. This is an image from Lucille Packard Hospital. The columns are all wrapped in displacement diffusers. Great for energy savings, great for reducing maintenance and financial incentives, really improving that indoor air quality that we see in all the other types of applications for displacement. Not typically seen in procedure rooms. ASHRAE 170 guidelines are a little bit different there, but in and outpatient rooms and things like that, that's still something that we see all the time. Hallways, all of that. So there's some examples really showcasing the improvement that we've seen with in-wall displacement diffusers right in patient spaces. So yeah, and then really tailoring again to like that LEED standards and energy efficiency codes that exist with a system like this. Banner Health facilities in Phoenix. So Banner Health kind of runs like 30 different hospitals. A great example of where they actually use displacement and radiant scattered throughout. So this is our ceiling diffusers there throughout their space for not procedure rooms, sorry, patient rooms and things like that. And it was massively successful. And they actually showcased how a bit of analysis of how displacement really minimizes CO2 concentrations and other particulates compared to a mixing system that they have in various different locations. So the idea here is really pushing that indoor air quality and different applications where you can use this. Yeah. Airports, we kind of spoke about this as well. Curved ceilings, overhead, incorporated within the architecture of the space, a really common application for displacement diffusers. So there's some example images right there. And I'll flip through a couple different examples of airports. All of these just really showcase the fact of incorporating it within your space effectively. Hidden away under shop rooftops and things like that, column wrapped, a lot of contaminants moving throughout the space. Easy type of system to incorporate and drive that to comfort and indoor air quality. So there's again another view of the San Francisco airport on the back there, incorporating within your space. Some more examples, and we see this all the time. Edmonton Airport has, the luggage racks and garbage bins and displays pieces, all kind of using displacement right within its space. So it's nice and adaptable. Internationally, we still see a couple of projects there that's using displacement, all kind of the same general idea there. Even Qatar. And that's an example of Edmonton International Airport as well. So you can see like the displacement on the stainless steel. So that's one where we can work with you, kind of really understand what the needs are there, even incorporate the plugins right incorporated in that space, in the diffuser itself. So easy to work with. Okay, so the last thing I want to do before I hand it off to Mike is really just speak to the value of CFD, mock-ups and things like that. really CFD is a tool to optimize your system. With us, we have a lab as well. We're actually able to optimize that even further by setting this up. And like you saw, we do these mock-ups all the time. That's something we do all the time to really verify and optimize our system. So with Displacement, it's a great tool to incorporate with CFD and really just get a lot of data outputs like this and showcase exactly how the system is working and moving to regulate your space, tailoring to that comfort. So just as a couple examples here of our mock-ups that we've typically done to showcase this, pull all that data in and apply it towards a CFD model and rerun it so that we can actually verify and test in our lab space that CFD output. And I'll just end here with showcasing our applications team. Our applications team is partially based out of Atlanta as well. And just to contact us, it's at displacement@priceindustries.com or stratified@priceindustries.com.
See us? We can hear you.
Yeah. Okay. Yeah, I could see the camera, and okay, good. So we'll get started. So just following up on what Narayan was talking about displacement, this will talk about specifically how do you verify your design, focusing on different displacement examples. So what I'm going to talk a little bit about today is just what I mean by CFD and what it can do for us. We'll talk about the importance of validation when it comes to CFD models. I'll introduce a couple of metrics for thermal comfort, indoor air quality, and then we'll look at 3 different examples, all displacement, and looking at specifically how we can use CFD to show us some of these comfort metrics and really to verify that design. So let's jump into it. So what is CFD? Essentially, it's a design tool. So it stands for computational fluid dynamics. And what it helps us do, it helps us get to a better performing design. And in a nutshell, what it does is it maps out the airflow patterns in the space, but also things like temperature, indoor air quality, thermal comfort, contaminants. I mean, we could do humidity as well. And it shows us that for a specific space. So when you're, let's say your whole project is an entire building, typically CFD is applied on one or several critical spaces within that building. So some examples Narayan already showed, it could be an auditorium, could be a lobby, maybe it could be a meeting room that's occupied quite frequently. But essentially what CFD is a risk mitigation tool for us, right? Because we're evaluating the design before it's built. So let's talk a little bit about validation. So this is how, if anyone asks, this is how do we trust CFD? This is exactly how. So the lab PRCN, over the last 15 years, we've done a lot of different types of validations within the lab, essentially doing measurements and doing a CFD model of the same space that the measurements were done in, and then comparing things like temperatures, velocities, or contaminant concentrations and making sure that the two match up, right? So that's essentially what we do when we talk about validation. And essentially a CFD model that's not validated is just an educated guess. So really it's the validation that gives us the confidence to use the CFD model for design purposes. Okay, so let's talk a little bit about the comfort metrics that I'm going to show to you today. The first one comes out of, the first 2 come out of ASHRAE Standard 55. If you've read through ASHRAE Standard 55, it's quite a page turner. There's a lot of different comfort metrics, but I'm going to really focus on 2. So one of them is called predicted mean vote. It's what's called a measure of whole body comfort. The way that it works is, let's say, you're all seated in a room. If I gave each of you a piece of paper, and then I asked you to rate your comfort according to the thermal sensation scale that I have up on the slide. And then if I were to average that score, that would be the thermal comfort for the room. So essentially what the comfort model does is it correlates that score to things that could actually be measured in the space, things like temperature, things like velocity, humidity, thermal radiation. So for example, if there's a solar load on the glass, as well as the properties of the occupants themselves, right? So how active you are and what you're wearing, and then it does a bunch of math with all those numbers, and then it spits out a PMV score so that you could use it as a predictive measure of how comfortable you expect your space to be. The other metric I'm gonna show is PPD, so it's percentage of people dissatisfied due specifically to ankle draft. And this is typically a metric that comes up for displacement systems because usually that's where you have, right, low level supply of cool air. And again, it's another model that correlates the PMV score and the actual velocity at the ankle level to a person's comfort. To pass, it has to be less than 20%. So essentially, it's going to tell you if your velocities at your flow level are too high and what they need to be to make sure that everyone is comfortable and not drafting. So that's on the comfort side. In terms of your indoor air quality, the metric I'm going to show is zone air distribution effectiveness. So that comes out of ASHRAE standard 62.1. So this is not just a metric, but it's actually a number that's used for your outdoor air design calculations. And essentially, it's a measure of how efficiently your system gets the fresh air into the breathing zone. And usually something called age of air, which is based on usually some sort of a contaminant concentration like CO2, is used to calculate it. And essentially, a perfectly mixed system, E sub Z is 1, right? It's about as high as you can get. Typically, displacement ventilation is above that because you get that thermal stratification. So the air that gets to your breathing zone is fresher than what's at the return. So that's why it's higher than 1. And when it's lower than 1, that implies that the air is not well mixed. So that could be, overhead mixing in heating, for example, if you have a very high supplier temperature. Okay, so now that we're all experts in thermal comfort and indoor air quality, let's look at some examples. So the first one I want to look at is an international airport in the Middle East. I believe it's still being built. Airports are a really good application for CFD because they're very, very big and very open spaces with high ceilings. So it makes a lot of sense to really just try to cool the occupied zone. This airport is really no different. You can see lots of curvature, very kind of sweeping architecture, very big open space. Definitely something that would be difficult to cool efficiently if you're trying to mix the entire space. So first, if we look at the results, let's look at the CFD model. If you've never seen a CFD model of a space, it looks like a Revit model, but ugly. That's how I like to describe it, because we take a Revit model and we simplify it down for the purposes of the analysis. And then the CFD software then calculates, things like temperatures, velocities, and other things at tons of points in the space and gives us lots of data. So this is the space we're looking at. We have different areas of the airport that we're looking at, including the ticketing and the security. And you can see we have low-level displacement diffusers, kind of tying it back to what Narayan says. It's typically built into the architecture. In this space, it's no different. There's kind of these little podium units where the return is up high on it and the diffuser is down low. So again, very much integrated in the architecture. Since it's in the Middle East, we have a very high outdoor design temperature, almost 120. I'd say pretty close to Arizona, probably, if you compare it to the US. Decent cooling load and supplier volume of just above 1 CFM per square foot. So in this case, we looked at kind of an initial design, or maybe like the engineer's first crack at designing this, and looking at a design when we modified it. So one thing we noticed every now and again is that the systems tend to be oversized for a lot of these larger spaces. Again, I guess they're trying to make them conservative, but this is where a CFD model can really help you fine tune the space. Now, in the first one, you might be tempted to say, Mike, that looks great. We don't have to worry about it. There's a lot of green, but it's actually overcooled. So if you look down into the occupied zone, you're kind of in the mid 60s for your temperature. And tying back to head to foot temperature difference, which, as Narayan mentioned, has to be within a certain range, we're well below that range. Now, what that means to me is that there's a lot of wiggle room for reducing air volume for this application. So if we go to the image on the right, you're seeing lots of red, but that red is near the ceiling, right? So we don't really care about that. What we care about is the occupied zone, where now you're roughly around the 75-degree range. And your head to foot temperature difference, again, within the occupied zone, is still well within that ASHRAE limit of 5.3 for seated and 7.2 for standing. Okay, so head to foot temperature is good. So what about thermal comfort? So let's look at PMV. So further evidence to show that the initial design, the space was overcooled. Our PMV is just below the comfort range, actually on the colder side. So people would feel slightly cool. And if anyone is wondering, we are accounting for the higher clothing level that you would see in Middle Eastern countries. So that is actually baked into that PMV metric, which is one advantage of using it. And you can see here when we decrease the air volume, you're seeing a lot less of that blue, a lot more green and yellow. So on average, the PMV is right within the comfort range, assuming the same properties of the occupants. So they're kind of moving around and they're wearing a certain level of clothing. So now, what about ankle draft, right? Ankle draft can be a concern because, again, we're supplying cold air at a low level. So in this case, you could see at the higher air volume, we weren't doing very well. There's a lot of red. So there's just typically too much air and the air is too cold. And then another benefit of reducing the air volume in this case, in addition to energy savings, is now where ankle draft is a lot more under control. You could see you still have a few red spots directly in front of the displacement diffusers, which is quite normal. But throughout the rest of the space, you're seeing a lot more like of your greens and blues, where you are well below the limits stipulated by ASHRAE. So, for example, if you average it out, kind of at that ankle level, 4 inches above the floor, you're at about 14%, right? Which is below the 20% limit. And finally, looking at indoor air quality. So this is interesting because, you know, conventional wisdom would say more air is better air quality, right? Well, in this case, our EZ is just above 2. In the initial case when we're supplying lots of air. And there's a little bit of a reduction when we decrease the supplier volume, but you can see it's actually not that much. And we're still above that 1.2 value that is typical for most displacement systems. So on the air quality side, we're actually doing quite well. So just to recap, we were able to reduce the air volume, right? So make the design more energy efficient just because the space is so big. While still being able to meet the comfort and air quality metrics for this application, right? So this is where the CFD is giving us the basically the validation that the design is going to work. So maybe a less architecturally impressive space, but still I feel pretty important. This is a school classroom. Displacement is used quite frequently in schools. So let's talk a little bit more about it. So pretty standard classroom. I think this one's about 750 square feet. In this case, we're looking at both cooling and heating. And in this case, I'm trying to remember if they're doing heating through the displacement diffusers. I think they're doing like just a little bit. So they're supplying air kind of at a neutral temperature. And the rest of the heating load, because this is a space in a Canadian climate, is being handled by a radiant floor. Now, that's not to say that that's all you have to do. It's just this is what they chose to use in the design. You could just as easily use a convector or radiant panel near the window to handle your heating, but this is how they're doing it here. And you can see a very respectable outdoor design temperature for heating of -26 Fahrenheit. Unfortunately, where I am, we're going to be hitting that within the next couple of months, so I'm not looking forward to that. So let's look at some results. So the first thing we could see is that at worst case conditions, we're actually just a little bit outside our comfort envelope, specifically in cooling and a little bit in heating. So in heating, you might even call that a pass just to say that it's close enough under worst case conditions. But in cooling, we're definitely higher than we need to be. So in this case, we could clearly see why. So I've labeled exactly where the window is just to showcase why that average value is so high. And that's because we're getting a lot of solar heat gain through the glass. So this is an example where we're not necessarily getting a good result, but it's actually showing us why, because we could see that there's solar heat gain through the window. So there's a few things we could do. One is we could just bump up the air volume, right, and try to cool it with air. Or the other thing we could do is actually do something with the window. So either add some sort of a shading, just like a roller shade, which would be a very inexpensive way to really cut down that solar heat gain. On the more expensive side, they could use better glass, right, that has a lower solar heat gain coefficient. So there are definitely some options. So looking at head to foot temperature difference, again, that solar heat gain is really not helping us in this case. So we have, even though we are meeting set point, you can see our head to foot stratification is just kind of on the, almost on the high side for the seated occupants. So we would definitely need to address that. And again, the two options would be either increase the air volume, and that would solve that, or adding some sort of treatment like shading to the glass would actually, so it would reduce the effective load in the space, and it would actually help with this as well. In heating, not as much of a problem, right? Because we don't have that solar load, so head to foot temperature difference really good. And you can see we clearly don't get as much stratification in heating, which you would expect, right? Because you have alternate systems that are active in addition to the displacement. Now, on the air quality side, we are doing quite well. So we're actually right above 2. And part of the reason for that is because we have so much stratification, right? Is because it's helping pull that air in a very efficient manner. So air quality wise, we're doing very good. Just a little bit of an issue with comfort. And on the heating side, a bit lower on heating on the E sub Z, again, because we're not just doing displacement ventilation, but we're pairing it with another system, right? So we're definitely not going to get that EZ of 1.2. Now, however, if you were to compare this to a mixing system, a typical mixing system in heating is usually around 0.8, right? So this is already a little bit better than that on the heating side. Okay, so let's look at one more example. This is a theater lobby. This is also in Canada. So again, very cold winter design temperature. It's a bit more of a complex example, but again, this really highlights where CFD can be useful to look at such examples. But we have a bit of a hodgepodge of systems that are conditioning the space. So you can see we have a ton of glass because it's a big open lobby. We have 2 levels, like a main level and a mezzanine level. So we have several systems that are helping us heat and cool the space. So for cooling, primarily we have low-level displacement, as well as we do have a radiant slab to help a little bit with the cooling. And on the heating side, the slab can be used for heating as well. And then just to give us some extra help on that glass, just to make sure we get air movement and no condensation, we have convectors kind of at the low level. And at the high level, we have slot diffusers that are blasting just alongside the glass. So they're not really designed to mix the whole space, really just to condition the glass and heating. And you could see that, again, tying it back to what Narayan was saying about heating with displacement, we got a little bit of a delta T on the displacement diffusers, but not very much. They're supplying about 70 degrees supplier temperature. And you could see that in this case, the cooling and the heating loads are actually quite high. And that's again because of this glass facade. And that's one of the reasons why we need not just the one system to do the job. So in this case, we'll just look at the ground floor. We could look at the mezzanine as well, but just for the sake of time, we'll focus on one. So you can see the PMV, we're not doing all that good on the cooling side. And this is again because of the solar heat gain on the glass. It's a little bit harder to control with just air. So in this case, for cooling, if we really wanted to make sure our PMV at worst case conditions is right in that sweet spot, we would need to either add a little bit more air or just bump up the capacity of that radiant slab or add some sort of shading to the glass, right? So again, we have some options. On the heating side, again, we're doing quite well. So we're right in that range. And again, that's because we don't have to worry about that solar load and heating. And also we're showing that the systems that we have, so that hodgepodge of systems that are all active, are doing a good job keeping everyone comfortable together. So if we look at thermal stratification, so again, this is where the solar load is kind of messing us up just because of all that glass. So our head to foot temperature difference is a little bit high in cooling. So again, we would need to address that by adding a little bit of extra capacity, either to the displacement or to the radiant system. However, on the heating side, we're doing quite well. So typically, this is a kind of a common theme comparing it to the last example, is that thermal stratification that's too high is not really much of an issue in heating, right? Because we have all those systems working together. And then finally, looking at ventilation effectiveness. So on the cooling side, we're doing extremely well. So we have quite a bit of air. There's, again, a lot of stratification that's helping us pull that fresh air towards the occupants. So our EZ is quite high. And in heating, even though the EZ is lower, it's still above 1. So we're still doing quite well on the heating side, even as far as indoor air quality. Okay, so hopefully that wasn't too fast for everyone. Just quickly summarize the metrics that we were using in this case to verify our design specifically for displacement is PMV and E sub Z. There's a lot of others we can put into the study. It's just these are the ones I focused on. And they can be easily implemented within the CFD model. And again, they come directly from ASHRAE standards because the CFD is giving us all those other variables. We would then, after that, use the same process to calculate PMV and EZ. It's a good cross-check to use for sizing your air handler, especially if it's a bigger, more complicated space to design. As you saw in the first example, the first design was quite a bit oversized, so there was opportunities for some savings. And really is an indispensable tool when the project is a bit on the larger and more complicated side, right? Like we could probably argue that maybe for the classroom, it wasn't as necessary to do the CFD. It was mostly done because it had that radiant component. But for some of these larger spaces, it does become quite important because the design can get quite complex. And really the main reason we're doing it is to ensure we do have a successful design in the end. Okay, so that's it for my part. I guess, how are we going to handle questions if there's any questions?
I don't see any in the chat. Does anybody have any questions here? Does not look like there are any. Oh, wait, we got one, Dave. Dave Guzlecki from HGA would like to know, is there a fee for your CFD modeling?
I would say typically yes. Depending on the project though, talk to Airflow Inc. There's something we can do for you depending on how big the project is.
So it depends, but there might be. Reach out to us, we'll work with you. Yeah.
If it was me and I was a consulting engineer, I would say this is the kind of thing I want to know in advance, got a complicated project, what's it be gonna be in a period of design fee? Sometimes these design fees are, they're never enough. But if you get in the design fee and you can narrow down your scope and have some guardrails around your design, I think there's a lot of value in that. Oh, sorry, thanks. I know it doesn't work like that, but oh, and A versus B, it would be hard to put. Mike, could you? So the question is, hi, it's Tom. Nice to see you.
Hey,
Hey,
Tom.
So Dave posed, hey, it's going to be a mixing system, but could we do CFD to validate whether DV would be a right choice in this case? And that might be something that we could evaluate without doing CFD as a preliminary and then validate it. Because I mean, if we did do, I'm answering your question, Mike, but if we did do a DV in place of a mixing design, we would have to come up with the savings that would be more than the cost of the CFD, but I'm sure we could. I mean, Stacy and I have done some designs where we significantly cut down the air handling size because of the DV application. And we caught it early enough that we could actually save money instead of just running the air handlers, down.
Yeah, I think you make a great point. the CFD is obviously a great way to like kind of give you that verification that yes, for sure it will be better than mixing. But I mean, I think for all the presenters in this room and I guess the ones remotely not in this room, like we've done enough of these projects where I'm sure we can do some hand calcs to figure out that DV would be a better choice for a particular space.
For that Google example, like that will Thanks. Hey, Mike, it's Ryan. So for the Google Bayview example, we initially were thinking a mixing system and stuff, and there was a bit of a team kind of collaboration there to understand what sort of loads, what sort of, what is the space used for, further conversation to kind of rule it down. And then when we did CFD analysis or a mock-up setup like that, we did kind of figure out that it was beneficial. So usually we're able to catch it up front, like Tom and Mike mentioned. Yeah.
Yeah, and I think the other thing maybe to add to that is that hopefully the CFD and the mock-ups we've shown speak to this, is that we've been pretty creative. Like sometimes there's perceived pains to installing displacement, right? Because it's low level, but there's ways to make some of those go away, right? Like we've shown, for example, you could do it, just that auditorium example, but others as well. Like you can install it up high, for example, almost like any other type of diffuser, right? So in terms of coordination pain, that could make that go away. So I guess just not to assume that it's got to be done the standard way every time, right? There's other ways to implement it.
Yeah, no, I think it's a great question though. So Dave was just saying that sometimes the owners don't want to be guinea pigs. And so you go through a bunch of exercises kind of for free as the consulting engineer. And then they go, nah. What I'd say to that is, and Mike, like I call up Mike all the time, Mike K, and just say, hey, a space like this, I called Mike when they built this big glass dome for Foxconn. The engineer didn't have any money in for CFD, but we just did a quick reality check because Mike's done a glass diamond before, or what was it, a glass prism? And we were just looking at airflow rates and deciding about, so Mike's he's seen hundreds and hundreds of different analyses, and he's kind of a little bit of a library of here's how this worked and here's how that worked. So what you can do is say, hey, what do you got that's similar? And then we can, maybe get started with the owner and say, this is what it's gonna look like. And then we will validate it.
Yeah, and yeah, I think that's a very good approach because, yeah, to your point, nobody wants to be like a full guinea pig, but I feel like at least by showing previous examples that are close enough, the owner might feel like less of a guinea pig, and maybe it might even push him to, put some money your way, you being the consulting engineer, to kind of maybe study it in a little bit more detail.
Okay, great. Any other questions? With that, I will turn it over to Caleb to put a bow on it.
All right. Well, thanks again to everybody from Price. And while it's great to have them here and they're always willing to come, it's even better to see this stuff, these smoke tests and everything in person. So in 2024, we're going to do 4 or so trips to Price. I think we've already sent out some marketing materials about the first one. So if you haven't signed up for that, please do. It is in February. If you've received an invitation, raise your hand. Those online, if you have. So we've. No, that's fine. Tom was just saying there's going to be 4 different trips. If you got the email, great. If you haven't, reach out to Airflow, send it to sc@airflowreps.com or clenhoff@airflowreps.com. We'll figure out how to get you those emails. There's a link to sign up. We're really excited about it. It's in February, but it's in Arizona. So if you want to get out of the cold, everything's covered. We only ask that if you do sign up for it, you commit to go. But other than that, there's no cost to you. We'll do something fun. We'll get a tour of the factory. Yeah, February, we're going to a Bucks game in Arizona, so it's going to be great. John Olson had a question. I don't see it on there. Oh, I think he just raised his hand. I said, raise your hand if you've got the email. Yes, and also I've been sending out some emails about the 2nd edition of the HVAC Engineer's Handbook that Price just came out with. So there's some people here that I'm handing them out to. If you'd like one of those, please let me know. We can get them personalized with your name on the front of it. If you just want one for your office, that's great too. We also have some new catalogs. So reach out to me. Again, my email is clenhoff@airflowreps.com. If you don't remember that, sc@airflowreps.com will work too, and then they can get that to me. So again, thank you everyone for attending and those that are here. Oh, wait, we got one more thing from Michael. So that was for the, yes. So we did hand out some tickets for those that those of you that were here who asked a question. Put your name on that. We'll get you your swag after that. So everybody online, thanks for attending. And we'll see you next year. We do have more trainings next year. Keep an eye out again for that schedule. Got some really exciting stuff coming up for 2024. So happy holidays, everybody. Happy New Year. And we'll see you next year.